Okay. So, I have this much of the playlist left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 videos. Most of them at least over an hour. Actually, hour and a half probably. Yeah. A lot of 3 hours. 3-hour videos. 3. And I gotta get this all done by the end of Friday. And I want to do a practice AP Calc AB exam. And then that'll be the end of this calculus arc. So,
Section 3.6.
binge today. See how long it takes me to get bored. But even when I do get bored, still watching. So, who cares, really?
This is basically using intercepts, like x and y intercepts, your relative max, relative min, which are your relative extrema, and your concavity to sketch a curve, to graph it, to see a really good approximation of what it looks like without a graphic calculator. Now, yes, your graphic calculator will do it for you, but to understand why these graphs are shaped the way that they are, you need the calculus. You need to really understand why they are the way that they are.
I probably won't be pausing the video much either.
Should we do an example? I'll tell you what I'll do.
Because I have a lot to get
I'll give
through.
you an example, and I'll give you the steps as we go through that. Would that help you? So here's your example. Here's your example. And I'll tell you how to do this problem verbatim, just exactly like you should, all right? With every single step. Step number 1, when you're graphing any curve, is, well, you want to find out as many intercepts as you can. X-intercepts and Y-intercepts. That's always a good thing to do, right? Because in most cases, that gives you at least an approximation of what you're talking about. Where you're crossing the Y-axis, where you're crossing the X-axis. So step number 1,
Okay, set y equal to 0 and x.
you're going to find the intercepts. By the way, how do you find x-intercepts? How do you find x-intercepts? Say it.
Y equals 0.
Y equals 0. So set the equation equal to 0. That's how you find x-intercepts. You set equal to 0, you solve for x. That's going to give you any roots. That's what a root was, right? When you set function equal to 0 and you solve for x, you're finding out where it's crossing the x-axis. That's the whole exact idea. Should make sense, right? Because if you set y equal to 0, that means you're going to find out everywhere you cross that x-axis. You believe me? Now, the y-intercept is quite a bit easier. By the way, you only do this step that's easy. Easy means it's quadratic or lower, or it's already factored for you. Okay, so cubics, don't spend your time factoring them.
This is why I want to pause the videos, but I really shouldn't. So to find the y-intercept, you set x equal to 0. To find the x-intercept, you set y equal to 0. But hold on, that would be like squared.
If I give that to you on a test, I'll just give you the x-intercepts. I'll say, here are your 3 x-intercepts. You follow me on that? So if it's easy, do that. Easy means, so I know this is recorded, so you don't cheat me. Easy means quadratic, linear, or if it's already factored for you, that's easy. Everything else, cubic or higher, is hard. Unless you can just see a root right off the bat, that would be considered easy. Believe me? Believe me? Okay.
Yeah, I'm confused today for some reason. Hold on. I'll just watch him do it.
For y-intercepts, how do you find y-intercept? Easy, really easy to do.
X equal to 0.
Set x, you plug in 0. You plug in 0 for x.
Wait, yeah, what am I doing? Hold on. I think I had it right the first time, yeah. Yeah. Yeah, I had it right. Okay. Make that way harder.
And it'll give you y-intercept. That's the easy one. That's nice. You all need to find that for every single one of these, if it exists. Let's try it. Let's try it. So this will be step number 1. I'll try to write out every step for you. Step number 1. Solving for x-intercept. How do you solve for the x-intercept? Well, this is just basic algebra. You're going to take your function, you're going to set it equal to 0, and you're going to solve for x. So we will have x plus 2.
We gotta verify it, right? Or what? Wait, hold on. -2 plus 2, 0. I mean, it's for this you wouldn't, I guess. It's already factored. Yeah, it's okay.
X minus 1 squared equal to 0. Can you find your x-intercepts from right there? That's great. That's great, because it's already factored for you. Can you tell me what's one of your x-intercepts? You'd have x plus 2 equals 0, x minus 1 equals 0, because it's zero product property. So x equals -2, very good, and x equals 1. You have 2 x-intercepts. Raise your hand if you feel okay with that. If this hadn't been factored for you, you just skip it. I'd give them to you, okay? Part 2 of step number 1 is find your y-intercept. Y-intercept says you need to plug in 0 for x and see what you have. So I'm going to take 0 plus 2 times 0 minus 1 squared. Don't forget to square it before you multiply. What is 0 minus 1? -1 squared
1
times
2.
is?
2.
You get 2. The y-intercept is 2. Do you feel okay for this so far? All right, step number 2.
For a second derivative
Step number
test.
2 applies only to rational functions. It does not apply to polynomials because polynomials do not have this. I'm going to put step number 2 and a little asterisk. The asterisk means for rational functions only. For rational functions, a lot of times with rational functions, you're going to get some asymptotes, right? You're going to get some holes. So for rational, polynomials don't have those. It's continuous everywhere. You don't have asymptotes, you don't have holes. So this is why it's only for rational functions. You're going to find all the asymptotes, vertical and horizontal, and any holes. Do you remember when vertical asymptotes exist? Denominator equals what?
0.
And you can't,
Factor.
when do holes exist?
When you can factor.
Okay, so denominator equals 0 gives you asymptotes or holes. If you can cross it out, it's a hole. If you can't cross it out, asymptote. Vertical asymptote, denominator equals 0, non-removable. Hole, denominator equals 0, removable. How do you find horizontal asymptotes?
It's that thing where you like look at the numerator and denominator you look at the leading coefficients. And you see which one's bigger. Which one has the bigger
Good thing you covered that
exponent.
stuff. Horizontal asymptotes occur. That's what the whole last section was about. It said, can you find the asymptotes as we go to the right, as we go to the left? That's what we were finding. We're finding horizontal asymptotes at zeros or at ones. That's what that did. And so what we're going to do here for horizontal asymptotes,
Wait, really?
you take the limit. Some more? You take the limit as we go x approaches infinity.
I completely
or x
forgot that,
approaches
jeez.
negative infinity. You have to do both of them
That is not
because
good.
you know the limit could change. Remember that 1/3, right? It could change, so you got to be careful on that. Take the limit. So, do we need to do step number 2 for that problem? Is it rational? So if it
Yep.
doesn't have a denominator, we're not going to be able to do that. If it had a fraction, you had denominator with a variable down there, then of course we would be doing that. But right here we don't. So now we're going to go on to step number 3. Step number 3 is you finally get to do some calculus. You're going to do the first derivative test. You remember the first derivative test? You had a whole homework section on that, right? First derivative test, you said equal to 0. It will give you 2 things. Critical numbers and increasing, decreasing. And that's what you care about, right? You care about where are my maxes, my mins, how am I going up, how am I going down. That's what you care about.
You have to use a product rule for this one.
First
wouldn't you?
derivative test. Why? Because it's going to give you critical numbers and increasing, decreasing. Or areas where the graph will increase or decrease. Hey, let's try that now. We'll get, you know what, maybe I'll give you all the steps and then we'll go through it. Step number 4. Sorry, I'm kind of backwards. 1, 2, 3, just pretend we're reading a book backwards or something. Step number 4, after you do the first derivative test, what do you think you're going to do next? Geniuses. The second derivative test. What does the second derivative test give you?
Rate of change of the rate of change. And inflection points.
Yep, the reason why you do it, just like Scott said, you can do for concavity and for inflection points. Step number 5, remember the table I had you make that has the first derivative on the top, second derivative on the bottom, that tells you increasing, decreasing, increasing, all that stuff, and it tells you concavity. So basically, it gives you a picture of your graph right there. That's what you make. So make the table.
These problems are getting very intense.
You know, they're very long problems. Especially, oh my gosh, especially with rational, they take a long time, a very long time. They're not easy. Well, actually, they're not hard. They're very time consuming. So they're going to take a long time. Not going to lie. Number 6. At this point, you're going to have everything you need, all right? You're going to have your intercepts. That's huge. You're going to have any asymptotes. You'll put those on your graph. You're going to have any holes. You put those on your graph. You'll have your critical numbers and your inflection points. What you won't have is the actual points, right? You'll have
So you guys start
critical
plugging in
numbers,
points to the
plug
original
them in.
function, right?
Find all possible points, relative ranges, relative mins, and inflection. Find your points from the original function.
Oh yeah. Because you get like the x for the y value, you gotta plug in, so you can get the coordinate.
The last, if you get the points, you get all the areas of increase and decrease concavity, grab it. Okay, we're going to get at least the first 2 tests done on this thing. We already have the intercepts. We got x and y. We don't need to do step number 2 because they're not rational. We're going to do the first derivative test. Now, don't fool yourself here. Yes, that looks pretty nasty. That you say, oh my gosh, that's a product rule with a chain rule or a general power rule in it. That could get pretty hairy and then have to set equal to 0. Or maybe be a little bit smarter about that. Probably easier to distribute that, right? Maybe distribute some
True.
of those easier ones first. That way you don't have to do all those rules. Now, if it was to the 6th power or something, firstly, that'd be insane. But secondly, you wouldn't want to do that. So just go ahead and maybe distribute that. So why don't you try that right now? Hopefully you got that. Did you get that?
Yep.
Okay, keep working. Step number 1, we got. Step number 2, we don't need it. Step number 3. Firstly, were you able to get that? How'd you have you were? You able to get that? Yeah?
Yeah.
Take the first derivative. Do the first derivative test. Go for it. By the way, that is a whole lot easier to take a derivative of than that, right? Try that on some of those graphing ones. Right? That's usually going to be something doable for you, at least doable. So try some of that. So take the first derivative. Let's do that together. Everybody, what is the first derivative when I do that? What was that? What do I do for first
Oh, I
derivative
didn't
test?
subtract the exponent.
If I set that equal to 0, I'm going to get x equals, well, I'll show the work on that if you really want me to. This will be 3x squared equals 3, x squared equals 1, x equals plus or minus the square root of 1. X equals 1 and negative 1. You okay with that so far? Okay. Hey, that's the first derivative test. That's not too bad. Let's do step number 4. Step number 4 is, can you do the second derivative test? Second derivative test says, well, take the second derivative. Go ahead and do that now. Take the second derivative.
It's just 6x,
How much
right?
is the second derivative? Oh, that's beautiful. I love that. What do you do with that 6x? When you solve for 0, what are you finding here?
Inflection? Or possible inflection point.
You're trying to find possible inflection points. So when you divide by 6, x equals 0. These right here are your critical numbers. This right here is a possible inflection point. Let's recap for just a second before I start making the table for you, and then we'll do the table next time. How many people feel okay on finding the x and the y intercept? Feel all right with that? Good, that's our basic algebra. Do you feel okay with our first derivative test and our second derivative test? Raise your hand if you feel all right with that. Now, step number
Stuff down,
5, this is where all your work happens, okay? All your work happens right here in step 5. You're going to have what you got from your first derivative, you're going to have what you got from your second derivative, and you're going to put all of it on something that looks almost like a graph. It's a number line. What were our critical numbers that we needed? What were our critical
Plus or
numbers?
minus 1.
So, -1, +1, 0 goes on the bottom. Why does 0 go on the bottom? Okay, so critical numbers went on the top. That was our first derivative. That's what we got, right? Possible inflection points, that's from our second derivative. That goes on the bottom of our table. It has to be in order, -1, 0, 1. Do you feel okay with that so far? What do you do now?
Start testing numbers on either one, pick one section.
So every single interval here, you follow? What number are you going to check here?
Negative.
And where are you going to check it? In the first derivative. What are you going to check here?
4, 12,
What was
minus
it?
3, positive 9.
-1 would work, right? It doesn't matter. -1, you're going to check it in
2,
the...
12,
Okay. Why don't you go ahead and do
positive 9.
that? Fill that table out for next time, because that's where I'm going to start next time. If you want to hang out for a second, I'll do it
So
right now, okay?
increasing,
For this
decreasing,
one, if I plug in f prime of
Slope.
-2, if I plug in f prime of 0, I can do that, and f prime of 1. I'm doing my first derivative. I'm going to get positive,
concave down,
I'm going to get
increasing,
negative,
decreasing,
and I'm going to get positive.
at 0,
That means increasing, decreasing,
increasing.
You follow me on that? Yes or no?
Yeah.
Okay, second derivative.
Still
I try
decreasing,
f double
increasing.
prime of -1. I try f double prime of +1. Remember, it's just this interval. It doesn't mean you can't plug those in for your second derivative. That's okay. -1 gives you negative, concave down. +1 gives you 6. That's positive. Concave up. Show of hands, some people feel okay with their concave down, concave up. That right there is a picture of our graph. We're done with step 5. This basically tells you up, down, up. We just have to find some points, and we'll graph that next time. Let's finish that problem. We're dealing with basically just a polynomial. We know that we can take a first derivative pretty easily if we distribute. We've already done that. We found first derivative test, second derivative test. We have our intervals of increasing, decreasing, intervals of concavity up and down. We also have our relative, which one's this, max or min? Relative max, relative, and good, inflection point. What we don't have is actual points, right? We need the points now. So the steps that we haven't done, after you've done your first and second derivative test, you've made me the table, what I want to see is your points. Now, I know
Okay.
the x-intercepts automatically give us some points. Basically, 1, 0, -2, 0, those are my x-intercepts. My y-intercept will give me another one.
Wait, is it -2? I thought it was -1. So it's right there, right?
0, 2.
Or no, he has 1, -2. These are for the first derivative, that's why, okay. So you gotta find -1, right? Come on. -2. -1, 0. 1. Is that it? That seems about it. 0, 0, 2, 1, 0. So we just have to find -1, right? It's 1 times 0. It should be 0.
So x-intercept, y-intercept.
Or wait, is it in? It's gonna be negative. Wait, no. Positive 4?
But then all of my critical numbers, my critical points, like my relative max and min, that's more points. My inflection point, that's another point. So you need to also give me, are you okay on the 1, 0, and the negative 2, 0? It's my x-intercepts. My y-intercept is at 0, 2. That's what we got those from. We did that last time, right? If you don't remember that, look back at your notes or look at the video. We did that last time. Now, those were x-intercepts, y-intercepts. We also have relative max. We have relative min. And we're going to have an inflection point. Just one in this case. Can you please tell me what's the x-coordinate for my relative max? The x-coordinate for my relative max. Negative 1 would be the x-coordinate for my relative max. You follow? How'd you get the 0?
Plugged it into the original function.
Good. The original one is what gives you points. So to find our points out, you take the negative 1, plug it back up into here, or this one would probably be a little bit
It's
easier,
0.
and that will give you out the y
No,
value.
it's
You follow?
4.
That gives you your points. So this is going to be negative 1. Let's see. Negative 1 plus 3. 2. 2.
Wait, is it 2? I'm so confused. Negative 1
So, I don't know.
plus 3.
Plug it into this form.
Wait.
Over.
Okay, it is 4. Jeez.
Ish happens, right? It's all good. What's a little point between friends, huh? A moot point. Right. Okay, negative 1 plus 3 plus 2, 4. Find your relative min. What's the x value for your relative min, please? What is that? So I'm going to put a 1 here. How do I find the y value? Plug it in. That one's going to be, that one's 0. Inflection point. Can you please tell me my x-coordinate for my inflection point? 0, 0, comma. That's an interesting point, isn't it? Not only is it the
0, 2.
y-intercept, it's also the inflection point. So we have that point twice, not a big deal. You feel okay with the points? Here's how to label them on your graph. What you're going to do is just work your way down, just like we did with the process. Start with your x-intercepts. 1, 0, put a point.
2.
Negative 2, 0, put a
0.
point. Those are my x-intercepts. My y-intercept is 0, 2.
What is this?
Put a point. Relative max happens at negative 1, 4.
Don't put a... Maybe?
Put a point.
Okay.
Relative min happens at 1, 0. Put a point. That's already there. Now, here's how I like to label these points. Are you okay on, firstly, the 4 points that we get? I mean, we have 1, 2, 3, 4. We have 6 of them listed, but we have 2 pairs of points. Here's also what I like to do. When you have the inflection point, you need to label it inflection point. That way you see the change in concavity. So which one of these is inflection point? Well, it was the 0, 2 one. So I'm going to label that inflection point, just IP, just so you know it's IP. For your relative extrema, your relative max and relative min, what I like to do, for your relative extrema, just IP, just so you know it's IP. For your relative extrema, your relative max and relative min, what I like to do, I like to draw a little dotted line. So for my relative max, which is at negative 1, 4, I like to do that. That says I can't go above that. For this one, this 1, 0, that I know that was a relative min, right? I'm going to do this. I can't go below that. I know that my graph is going to bounce off of those dashed lines. Do you follow me on that?
Oh, wait.
That's what's going to happen here. It's going
This is
to,
relative
we'll
min.
follow in our graph. Go up, bounce off, hit an inflection point, bounce off, and then keep going forever. Does that make sense to you? So label those things with something like that.
Yeah,
Do the
I guess.
inflection point, changes concavity.
Makes sense.
Do your relative max, relative min, do little dash lines. That way you know you're not going to go past that. You're going to be changing at those values. So let's see if we can graph our graph. If we follow this table and associate them with these points, we should have a pretty good looking graph. It says you're going to start out, you're going to be increasing. Which way is increasing? This way or this way? This one. So we're increasing. How are we increasing?
Concave down.
Concave down. So increasing, concave down. Increasing, this is concave up, this is concave down. You follow? We're increasing, concave down. It says increasing, concave down. We're going to go through that point. So increasing, concave down. It's going to be hard to draw that way. I tried to do it. Increasing, concave down. Are you following me on this? I'm going to hit that, what it says, a relative max. Increasing, concave down, relative max. Then I start decreasing. How am I decreasing? Look at the board here real quick. How am I decreasing for this interval?
Concave down.
It says you're decreasing, but you're doing it concave down. You
Until
follow
x
me?
equals 0.
So for this little interval right there, it says x equals 0, right? It says from negative infinity to negative 1 on the x-axis, you're increasing concave down. From negative 1 to 0, negative 1 to 0, you're decreasing concave down. That's this way. Decreasing concave down. You still okay with that?
Oh wait, that's the.
Yes, no.
Okay.
After 0, it says I'm still decreasing.
Right, no, I did
on
that, yeah.
Concave up. That's like this. Decreasing concave up. So that was my switch in concavity. I'm still decreasing from 0 to 1. From 0 to 1, I'm still decreasing, but I'm concave up. As best you can. After x equals 1, that's why I made the point earlier in the class that you have to follow the x-axis, right? You got to be on that. So you go, okay, after x equals 1, I'm increasing again and I'm concave up. Increasing concave up looks like that. That probably should be a little bit more narrow. But that's the idea. Can you get this graph from this picture of the graph? How many feel okay with that? So follow along the x-axis, start from the left, work your way right, increasing concave down until x equals negative 1. Right there, we have the point for that. For that little interval, decreasing concave down. Right there. For this next interval, decreasing concave up. Right there. Last interval, 1 from x equals 1 on, increasing concave up, and we have our picture. Now, of course, it's just an x cubed, so we kind of have a picture of that anyway. But the double root's interesting, right? We were able to find that. We were able to find all these points. That's a pretty accurate graph. Fairly accurate. How many people feel just fine with it? All right. Now, I'm going to erase this because it's going to take us a long time. A lot of board space to do these problems. We're going to graph some rational equations. You ready for rational? Rational are harder. First, because the derivatives are harder. And second, because you have asymptotes. That's what makes them harder. So I'm going to try to get through 2 today. We have about 30 minutes or so, 35 minutes right now. So they take a long time. We're going to try to get through 2. Oh yeah, were there any questions on that? Now, the question is, do I do that on purpose? You'll never know. I'm not going to rewrite the steps because I gave them to you last time. They're on the video if you need to check those out again. The steps were 1 through 7. Number 1, x and y intercept. Number 2, asymptotes if it's rational. That's why we didn't have a number 2 up here. 3, first derivative test. 4, second derivative test. 5 is make the table up. 6 is make the points. And 7 is graph it. So we're going to follow the same 7-step process the whole way through. By the way, we are going to be dealing with some roots on this, so if you take your calculator out, I'm going to need some help calculator work from you on this. Okay, so x squared minus 1 over x cubed. Step number 1. Hopefully the algebra type stuff, you find your x and your y intercept. So we're going to do every step together here. X-intercept would happen where you set your function equal to 0. You follow me? Set your function equal to 0, and then you solve it. Well, if you set your function equal to 0, basically that's just where the numerator equals 0. The denominator equals 0 is undefined. So we really just say, okay, well, even if you want to think about it this way, multiply both sides by x cubed, you still get x squared minus 1 equals 0. What are my x-intercepts?
Plus 1 x
Say
minus
what?
1.
1 and negative 1. Very
Alright,
good.
yeah,
Add
yeah,
1,
yeah.
take square root, or factor. Either way, you're going to get x
True.
equals 1, negative 1. Are you okay with that so far? You sure? So numerator equals 0, no problem. That's how you find your x-intercepts for any rational function. Numerator equals 0. You got it? Now, y-intercept. Y-intercept says you plug in x equals 0 and you find out an answer. What do you get when you plug in x equals 0? Negative 1 over 0. That's a problem. That means there is no y-intercept. And we're going to find out why in step number 2, but it does not exist. I'm going to erase little parts so we save space. But this is from x squared minus 1 equals 0. That gives us the 1 and negative 1. Step number 2. Oh, step number 2 is a good one. Step number 2 is a good one. Step number 2 is where we find out all the
Those
asymptotes.
asymptotes.
Now, you might be thinking, who cares about asymptotes? Don't we have increasing, decreasing? The asymptotes tell you most of what you need to know for your graph. They really say, here's your sections.
Yeah, this is
Here's what
definitely
you're
gonna be an
do in those
asymptote.
sections. Basically, if you knew the asymptotes, you can almost guess what this graph is going to look like with just a couple numbers. So we're going to find our
Analysis,
asymptotes,
right?
both vertical and horizontal. How do you find vertical asymptotes?
Is this going to be a... The horizontal
No,
for this is
not
going to be...
derivatives. We don't do calculus till step number 3,
Zero?
by the way.
The denominator equals 0.
Good. When the denominator equals 0, you're going to have discontinuities, right? Those discontinuities are either wholes, if you can cross them out, or asymptotes if you can't. So you'd say x cubed equals 0, and x has to equal 0. Can you cross out the x cubed with anything? So then what that says is there's a discontinuity. A vertical asymptote occurs where x cubed equals 0. Or in other words, x equals 0. That's going to give us a vertical asymptote at x equals 0.
Then you just
Now-
plug in 1 and negative 1, right?
Listen carefully. If you were able to cross it out, you would do that. Okay, you cross out that discontinuity. You just keep in your mind that there's a hole there, all right? You'd have to identify the hole. So it's a little bit easier in asymptote. You'd cross out the problem. You'd say their hole exists at this point, and you put a hole in the graph. Does that make sense to you? That's what you would do. I think I've shown you how you do holes. I think I gave you x squared minus 4 over x plus 2. The hole would exist, actually minus 2. The hole would exist at what did I do plus 2? At 2. And then you would find that value, you put a little circle there, and it would just be an undefined little point. You follow me on that? Okay, so that's what you would do with holes. Most of the time, I'm going to give you asymptotes. Most of the time. You will have some holes. Most of the time, asymptotes. How do you
What about
find
positive?
horizontal?
Something like that.
Limit
Or what?
Yeah, you're right. A limit as what? So really, there's 2 of them, right? You got to check both. Don't just assume that it's going to be the same. A lot of times it is, but we've seen cases where you have different horizontal asymptotes. Hey, do you remember how to take limits of that stuff? I hope you do, because I think that's what your homework was on, right? Hope so. How do you take a limit as we approach positive infinity or negative infinity? Don't mumble it, say it.
Divide by the biggest. Divide by the highest power.
Very good. In the keyword, denominator, not numerator, denominator. So we would be divided by x cubed, both here and here. If we did that, it's going to look identical to this. You'll get x squared over x cubed minus 1 over x cubed all over x cubed over x cubed. Can you see that this is going to go to 0? Yes, no?
Yeah.
If you want the rest of it, here it is. I'm just going to do, I'm doing this one right here. You got 1 over x minus 1 over x cubed all over 1. True? Yes, no?
Yeah.
Okay. 1 over x cubed, 1. Tell me something, ladies and gentlemen. You need to know this. When x goes to infinity, what's this do?
0.
What's this do?
0.
What's this do? Stays at 1. That's 0 over 1. That's 0. Now, just think through it. Think through it. Is there going to be a difference if we go to negative infinity? This would still work, right? You still do that. You still have exactly this thing. You follow me? Now take
Yep,
it
it's
to
gonna be this
negative
one.
infinity. What's 1 over negative infinity? We'd be over here right now. What's 1 over negative infinity?
0.
It's still 0. What's 1 over negative infinity? It's still 0. This would still be 0, and that's still a positive 1. Because you're dividing x cubed by x cubed. No matter what it is, that's going to be a positive number, positive 1. You follow me on that? You sure? Yes, no? I see some nods. They're like, Questions? Are you okay that this is equal to 0?
Yeah.
Okay. If it was going to negative infinity, so let me just change the problem here. Now let's say, aha. 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 Does anything change? Is it still 0? So, where are our horizontal asymptotes?
0.
0.
Yep.
Both left and right? Both left and right. So horizontal asymptotes occur at y equals 0, both positive and negative infinity. Would you mind if I erased this? Do you need it? So I've taught you how to do the limits. You do the limits. Also, you're going to hate me for just telling you this, but you can see it just by looking at the limit. Where's the power bigger, top or bottom? That's something over infinity, right? That's going to be 0. Where's the power bigger, top or bottom? That's something over infinity. That's going to be 0.
However you want us, if.
I want you to show it. Yeah, I want you to show it. Yeah, but at least you can check your work really quick, right? So this means as we're going to the right, we're going to 0. It's going to the left, we're going to 0. How many people feel okay with what we've done so far? Any calculus? Not really, just limits. Let's start
Wait, how do
doing
you
our
check
top or bottom. That's something over infinity. That's going to be 0.
However you want us, if.
Yeah, just by looking at the limit. Where's the power bigger, top or bottom? That's
Oh, yeah,
something
like
over infinity, right?
That's what I was saying.
That's going to be 0. Where's the power bigger, top or bottom? That's something over infinity. That's going to be 0.
However you want us, if.
I want you to show it. Yeah, I want you to show it. Yeah, but at least you can check your work really quick, right? So this means as we're going to the right, we're going to 0. It's going to the left, we're going to 0. How many people feel okay with what we've done so far? Any calculus? Not really, just limits. Let's start doing our step number 3. What's step number 3? Let's do our first derivative test. Now, I know you all know how to take the first derivative, so I'm going to start doing these first derivatives a little bit quicker. Just stick with me on these derivatives. What you would do, take your quotient rule, and you're going to have this minus this. All over that square. Still okay so far? Actually, I'll show the work if you really want me to. Low D high minus high D low, square the bottom, and we're okay to go. X cubed times 2x minus x squared minus 1 times 3x squared all over x to the 6th. Yes, no? Okay, so basic derivatives actually. What you do with them later is kind of sucks, but basic derivatives so far. Y prime equals 2x to the fourth minus 3x to the fourth plus 3x squared over x to the sixth. So far, so good? Distribute, deal with those signs. You see where the plus is coming from, I hope. Y prime equals negative x to the fourth plus 3x squared all over x to the sixth. Can you keep going? Can you factor, simplify? Yes, factor out an x squared. That is going to make your work later easier.
This goes away. Perfect.
Would you agree that that is your first derivative? Ladies and gentlemen, are you okay on your first derivative? I've gone kind of quickly through that, but I'm assuming that at this point you can do a quotient rule and simplify it. You follow me? Nudge if you feel okay with it so far. Yeah. What is this? I know it's the first derivative. What is it?
Increasing or decreasing.
It's going to give us increasing, decreasing because this is a...
Or not concavity.
It's a slope.
Increasing, decreasing. Yeah.
And if slope is positive, you're increasing. Slope is
Forgot
negative,
he's on the
decreasing.
curve.
Slope is 0, you have a potential relative maximum in. You follow me? So what we're going to do for the first derivative test is you go, okay, now I want to set this equal to 0. And what we're going to do on this is pick out all the points that are undefined and all the points that have a 0. So can you please tell me for my critical numbers, that's what we're talking about here, for critical numbers, the first one I see is x equals 0. Where am I getting x equals 0, ladies and gentlemen? That tells you that, right? That says x equals 0 is an undefined point for your slope. That could mean that you're changing between increasing and decreasing. Does it have to? No, but it could. It could mean that. Do you follow that? So you have to have the x equals 0. Make sure you have where the denominator equals 0 on your critical numbers and for your inflection points later. You've got to have that. Secondly, you're going to set the numerator equal to 0. That's the same idea as over there. It's very much like finding roots. Numerator equals 0 is going to give you the actual numbers that makes your slope equal to 0.
Does it get worse
You follow
after
me
you
on that
find
one?
the second derivative?
Okay, so if you want to multiply by x to the fourth, you would see the same thing, wouldn't you? Wouldn't you? Okay. How do you solve that?
3 over.
I would probably add x squared and then divide and then take a square root. And you could subtract 3, divide by -1, take a square root. It's just more work. But you're going to get somehow you're going to get x squared equals 3. True? Well, that means that more critical numbers occur at plus or minus square root of 3. So I have x equals 0, x equals root 3, which is why I had you take your calculators out, because I can't do that, and negative root 3. Those are my critical numbers. You okay with your critical numbers? Yes, no? You take a square root of 3. You have 3 and root 3. 1.7 something. What's next? Now, the reason why we simplified this as much as possible is for our second derivative. Let's go ahead. I'm going to do the second derivative. Why don't you try on your paper as well, see if we can match up with the right answer. So step number 3, sorry, step number 4 is our second derivative. Second equals, you're going to get just more work. And you got to have that. Second tells you critical is x equals 0. Where am I getting x equals 0, ladies and gentlemen? That tells you that, right? That says x equals 0 is an undefined point for your slope. That could mean that you're changing between increase and decrease for your, like find second derivative.
Okay, you got something completely different. Okay. Or no, he didn't. Kind of, he did.
That's not as bad as you thought, huh? Hopefully not as bad as you thought. Did you get that far?
Oh, you know what? I
If you're
added
still going, still go. That's fine.
I added the exponents instead
Distribute,
of
combine like
distributing
terms,
it.
factor, simplify. You're going to get down to that point. Let's all make it down to this point. Are you okay that that is your second derivative? You know how to do the second derivative already. That's not the issue with this problem. Okay, I know you know how to do that. Your point now is, let's find our possible inflection points or the numbers where we are going to change concavity. Can you tell me from here the numbers where I'm going to change concavity? I'll tell you one of them. So possible inflection points. I'll tell you one of them. One of them is x equals 0. How am I getting x equals 0? Yeah. In fact, you know what? That's kind of a key point for us. That was an undefined point from the very beginning, right? If you take a quotient rule, look at that. It's going to come back again because you're just squaring it. Take a second quotient rule, it's going to come back again because you're just squaring it. So that's going to be undefined. It's going to be a critical number. It's also going to be a possible inflection point where we change concavity. It shows up a lot in our problem. You okay with x equals 0? Now, the factoring is nice for us because it says if you set this equal to 0, which is what you're supposed to do, you can clear out the denominator. We had to include that point because it did make an undefined second derivative, so we do have to include it, the x equals 0. But now you can say, 2 times x squared minus 6 equals 0. You set the numerator equal to 0. Are you with me on that one? Yes, no? Okay, but the 2, does the 2 do anything for you? So if you divide by 2, basically you're going to get x squared minus 6 equals 0. You're going to get x squared equals 6. And you're going to get
Plus root square root of 6.
okay, yeah, I understand. Not very nice numbers, I get it. But can you find them?
Yeah.
Now, the point is, as soon as we do our first and our second derivative, we're going to make our table up. From our first derivative, it said you're going You're going to have something special happen at the 0 maybe. You're also going to have something special happen at the square root of 3 and the negative square root of 3. Are you okay with the points that we got from the first derivative, everybody? Are you all right with that? Negative root 3, 0, 0 especially, and the root 3. Are you okay with that one? Now the next one says, okay, you still have from our possible inflection points, 0. Then you have root 6 to the left or to the right of root 3. It's actually pretty important to put this in the proper order, right? So you have to have root 6 over here somewhere. And negative root 6. Now we're going to do what with this? After you find those numbers, are they hard to find? Not really. Not really. What do you do now? After you have the negative root 3, 0, root 3, what do you do?
Plug them into the derivative.
Wait, plug that in?
Yeah.
That's going to give you 0.
Test them in the original function.
If I plug that into the original function, that will give me points, which I'm going to have to do in step number 6.
Numbers between intervals.
What is my class is
Yes.
falling apart?
Look, you need to know what happens here.
Oh my
You know what
goodness.
happens here, 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 here. All those little intervals, right? You got to know which area to plug him into. Where am I going to plug in points from all these 4? That's why we have that first derivative, and these are going to go into the second derivative. So let's go ahead and try that. For this one, I'd plug in negative 2. I'd plug in negative 1, 1, and positive 2. We do it in the first derivative. So if I plug in negative 2 here, so f prime of negative 2, f prime of negative 1, f prime of 1, f prime of probably positive 2. I don't really care about the actual value, all right? I really don't. I care about the sign, positive or negative. So we're going to take negative 2, plug it into the easiest one to work with. That's this one. If I take negative 2, I know I'm going to have negative 4 plus 3, that's a negative number over a positive number. Did you get a negative as well? Yes. Negative. Hey, what's negative mean in relation to this? Decreasing, very good. Because it's a slope, negative slope means decreasing. Plug in negative 1. If I do negative 1, I get, remember that you don't square this negative, right? That says negative x squared. So this will be negative 1 plus 3, that's 2, over, it's positive. What's positive mean? Increasing. Don't just say up, because that could be misconstrued as concave up. I want to say increasing or decreasing. How about 1? Let's try 1. If I try 1, do you see I'm going to get the same exact thing as negative 1? Because that says negative 1 plus 3. That's positive over, that's positive. So,
It's not a critical
is
point.
that
It's 0.
a relative extremity? This one.
No?
No, that 0 actually didn't change, right? We're increasing and increasing again. That's interesting. How about that, the 2?
Probably
It's gonna be
decreasing.
negative. Yeah, for sure. You plug in the 2, you get
Or what?
negative over positive, that's a negative.
Okay.
Now let's try our second derivative. If we do, for those of you who really have the hang of this, can you do me a favor right now? Can you start finding me points? I think I can pretty much take care of the 0, but I'm going to have a hard time plugging in the square root of negative 3, root 3, negative root 6, and root 6. So if you want to try this as I'm going through the second part, if you really get to grasp this. Left side of the room, my left side, you guys try the root 3 and root 3. You guys try the negative root 6 and root 6 in the original. Okay, can you do that for me? Give me to like the first, I don't even care, the first decimal place is fine, 2.5 or whatever. Now, for our second derivative, we're also going to try some values in these intervals, but you're going to plug them into the second derivative. So f double prime of, that's going to be like negative 3. Double prime of negative 1. Double prime of 1. Double prime positive 3. If I do that, if I take the negative 3 over here, that's going to be a positive over a negative. I have a negative. What's negative mean, by the way, when I'm talking about second derivative? Concave down. If I plug in negative 1, notice what we do. We've got 1 minus 6, that's negative 5, over negative.
It's gonna be a negative.
That's going to
So
be
it's,
that's a positive.
Wait, what? Wait, how? Or wait, the to the 5th, yeah, okay.
Concave up. If I tried positive 1 here, I'm
Probably
going
gotta
to
be a
get
positive.
a negative over a positive. That's going to give me a negative.
Oh, wait. Oh. No, I suck.
And if I try 3, I have a positive over a positive. That's going to give me a positive. By a show of hands, how many people feel okay with our
So it's gonna look
concavity
like-
at this point? Right? Are you guys okay with this? You guys over here? Yes? No? So we've checked this in the second derivative. We got this was a negative interval, positive interval, negative interval, positive interval, concave down, up, down, up. Were these inflection values? Does concavity change here? And here? And all of them. Actually, we had different concavities. Step number 6 is you have to find all of your points. So right down here, I'm going to write my points. I know for my x-intercepts, I'm going to be at 1, 0, and negative 1, 0. My y-intercept, I didn't have any, so that just came from my x-intercepts. Now, I also have all this junk over here. So my relative max and relative min, can you tell me which one of these is going to give me my relative maximum? My relative maximum, is it going to be a negative root 3 or the positive root 3? Positive.
Crap.
This one's going to be a
Okay.
relative minimum. So relative max relative min. The relative max will be at square root of 3 comma something. I don't know what it is. Negative square root of 3 comma something. Somebody plugged in the square root of 3. About how much did you get? 0.38?
Yeah.
Okay, so let's say 0.4. Is that negative 0.4? Okay. Are you okay getting those numbers? Do you remember where I'm getting these numbers from? Where do I plug in the root 3's? Not the first derivative, not the second, but the original function is going to give you points. Are you okay on that so far? You sure? We're almost done. Almost done. Now, let's do the root 6's. The root 6's are my inflection points. Negative square root of 6. And the square root of 6. Somebody plugged in the negative square root of 6. How much do you get?
1.
Now, this is everything that you need in this little block to graph this. So I'm going to erase this because we don't need anymore. Get everything. Well, almost everything. I'm going to leave the asymptotes because I need those. That's going to be important. You're going to kind of see what I want from you on this. The first thing that you should do, put out your asymptotes, wherever those things are. So my asymptotes are at x equals 0, x equals 0 horizontally, both right and left, and, I'm sorry, y equals 0, both right and left, and x equals 0 for our vertical. So we know we have some asymptotes. Next thing you do, put down your points. Your x-intercept is at 1, 0, and negative 1, 0. Your y-intercept, you don't have one because you have an asymptote there. You don't have that. Your relative max and relative min. Square root of 3 the square root of 3 is about 1.7, somewhere around there. So the relative max occurs at, okay, so there's a slight error
Oh, he messed up.
in class. The numbers that some of the students gave were a little bit off. Here's the correct numbers. Now, we went through this a couple times, so of course, if you watch the video, you're like, whoa, what's going on here? Why are these numbers changing? Here's where the number's changing. When you take the root 3 and you plug it into the original equation, which gives you points, what you actually end up getting is 0.38. If you take negative square root of 3, plug it into that original equation,
They
you're gonna get
rounded?
negative
Bruh.
0.38. Now, when you take the square root of 6, you plug it into the original function, what you're going to get is
Let's hop back
0.34
into it.
and negative 0.34. They're very close points. Now the graph's going to look somewhat similar, but you'll notice that on the video I have that as 1 and negative 1. If you just change that to 0.5 and negative 0.5 and just extend the graph even further, this is about what it looks like. The picture of the graph on the video is just fine. So here's what you would end up doing. You would still have your same x-intercepts. You would have your relative max and your relative min. You would have your inflection points. They're just really close together. So our graph, as you can see, we're still decreasing. That's what this means right here. Decreasing concave down. So we're dropping and we're concave down. That's this way. Also, we have this horizontal asymptote. That was so important for, was to tell us that our function is not going to be going way up like this, and I can go way down like this. It's going to be riding along this x-axis. So it must look about like that. Not exactly like that, but pretty close to that. Then from this point to this point, that's this little interval. It says you're still decreasing, but you're concave up. Your slope is starting to increase. Your function's still decreasing, but your slope is getting more and more, it's getting larger and larger. So we're going to decrease concave up, and then right after that point, right here, it says you're still concave up, but now you're starting to increase.
Man, I'm gonna be real. I hate this lesson. Oh my goodness.
Increases all the way up until you
I
get
just want to
zero.
move on the
Now,
integrals.
At x equals 0, you have a vertical asymptote, which means that you're never going to reach this y-axis. All that's going to happen is if you're still increasing, as you get closer and closer, you're going to shoot up to positive infinity. So that's what the horizontal asymptote said. It says you are increasing. You can't be decreasing. You're increasing all the way up until x equals 0. That says horizontal asymptote.
Wait, what is this? Relative min?
And you're concave up the whole way. Now the other picture, it's going to look very similar to this, only kind of rotated a little bit.
It's relative max.
Starting from 0, you're increasing and you're concave down. That's this way, increasing concave down. Now because again you have this vertical asymptote, the only way you can be increasing and concave down and have this vertical asymptote is by shooting up just like this. You can't come down, that would be decreasing. So you're coming up like that. Coming up just like that. Now we reach this point, that is our relative maximum. It says at your relative max you switch from increasing to decreasing, but you're still concave down for that whole interval. So increasing to decreasing, but concave down. That's that little point right there. After that point, it says you're decreasing for the rest of your graph. You're decreasing the whole way, but now you're concave up. The only way we can decrease the rest of the way and be concave up and associate this horizontal asymptote is by putting it right along the x-axis, just riding that thing all the way out. And that's the same picture that you have on your graph. That's an inflection point. Now, how in the world does this graph look? That's why I have the table. This is pretty interesting because we're going to associate all this stuff with our asymptotes. Now check it out. You know that this has to go close to this one, this has to go close to this one, has to go here somewhere and there somewhere, right? Now here's what it says. It says you're going to be decreasing. Decreasing is like this, and you're going to be concave down. That's this way. Does that make sense? All the way until you get to this point, that negative root 6. That looks like this. Decreasing, concave down. Do you follow me? That's the only way you can have it. If you're decreasing concave down up here, you fail the asymptote. You have to be with the asymptote. That's why asymptotes are important. It says you're going to be at that asymptote right there. You see what I'm talking about? Okay? From here to here, this little interval says you're decreasing, but you're concave up. So this part, decreasing down. This little part, decreasing up. That's the inflection point coming back at us. That's this. That's concave up. You see the decreasing concave up? Then this part says increasing concave up. That's this way. And you actually do that all the way to 0. Now, how do we go all the way to 0? Where do you think this is going? If it's increasing and there's an asymptote, does it magically go back down here? Otherwise, we have another relative max, wouldn't we? It's going to go all the way to infinity. There's an asymptote, folks, an asymptote. It has to go to the asymptote. So if it says increasing, concave up to 0, it's going like this. Forever. Is there any other way that it could be and still have the asymptote? Nope. Now, the rest of it, the other side of the graph. The other side of the graph says, for this interval up to root 3, you're increasing, you're concave down. That's this way. You follow? Increasing concave, but you also have an asymptote, so you have to meet the asymptote. Increasing, concave down. That's increasing concave down until you reach a relative max. You know that's a relative max. Then it says for this little interval, you're decreasing and you're concave down. Decreasing and concave down. That's this way. So for here, you're going to go, oh, down. And then from here on out, after that root 6, remember that's our root 6, you're going to be decreasing, but you're concave up. That's this way. And you have to meet that asymptote. That's there. As good as we can do. But that's a pretty darn good graph for just having for no graphic calculator. That's pretty good. How many people were able to follow that? Now, you got to be careful. Be careful with these numbers. You messed me up. But that's okay. Be careful with your numbers of your own. Now, we only got through one example. If you want to hang out just a little bit, I'm going to try to do one more. All right, we're going to do one more example. How to graph some rational functions. I'm going to try to go all the way through it, but I'm going to be erasing things as we go. So it might help you to write this down as we're going through it. That way, when I erase it, you're not like totally lost. So I'm going to save some space. I only have a limited board to work with. So let's start with our x and y intercepts. That's always step number 1. X-intercept says, where is the numerator equal to 0? That's the only places where this function can actually equal 0. If the denominator equals 0, then we're undefined. We have either wholes or asymptotes. So in our case, x-intercepts are add 8, divide by 2, take a square root, plus and minus 2. A little bit lower. Okay, y-intercepts. You plug in x equals 0. What you have is 0 minus 8, 0 minus 16. Negative 8 over negative 16 is positive 1/2. Vertical asymptotes, those occur where your denominator equals 0 and you can't cross it out, you can't simplify. If you were able to simplify it, it would be a whole. But if you're not able to simplify it, that's a vertical asymptote. So when we have this denominator equal to 0, again, well, it's different squares, you can factor it, you can add 16, take a square root. Either way, you're going to get x equals 4 and negative 4. Now, x plus 4 and x minus 4, they do not simplify with our numerator. That means they're not wholes. They are, in fact, asymptotes. All right. Now, as far as our horizontal asymptotes go, that says what happens when we take x to infinity and negative infinity. And that's dealt with a limit. If you notice that we have our leading terms, polynomial here, the powers are the same. So when you do that whole divide by the largest power in the denominator,
two.
you're going to divide by x squared. What that's going to give you is 2, 0, 1, 0. So basically you have 2 over 1. That's going to be 2. Also, notice that it doesn't matter if I have negative infinity either. You get the same exact thing. What that means is we have a horizontal asymptote at 2 to the right and 2 to the left. So I'm going to erase this now. We know our horizontal asymptotes are at 2 either way. Y equals 2. Now, as far as our first derivative test and second derivative test, here goes our derivatives. Try to follow along. Again, I'm going to erase this when I'm done. That's our first derivative. Now, what the first derivative says is slope. Where slope is positive, you're increasing. Where slope is negative, you're decreasing. Where slope is 0, you have the potential for a relative max, relative min. Or something interesting could change, maybe around an asymptote or something, change from increasing to decreasing. We've seen that before. So the ideas are find all the places where the numerator and the denominator equals 0. So in our case, the numerator equals 0 when when negative 48x is equal to 0. That says x equals 0. That's going to be one critical number. That possibly is a relative max or relative min. Now, where the slope is undefined, it's not necessarily a critical point, but it could change from whether the graph is increasing to decreasing or vice versa. So, in our case here, hopefully you can see this. Denominator equals 0 when x is 4 and negative 4. It's not coincidental that that's our vertical asymptotes. Those points can come up again, especially with the quotient rule, when you notice you're just squaring the denominator. So 3 critical values that we're going to be putting on our first derivative table. We've got our 0, our 4, and negative 4. Take a look at this. Hopefully you've written this down. I'm going to erase this right now and write it right up here. That way I can work on my second derivative. And what we got out of that again was 0, 4, negative 4. Okay, second derivative test was going to give you concavity. So let's take the second derivative, see what we get. Again, write this down, I'll erase it when I'm done.
Man, I am not doing all that, honestly.
This is going to be to the fourth power since we're squaring that square. Notice the plus, I'll change that right now, just make a negative into a plus. Also, I'm going to take a shortcut here. I know I tell you not to do this, but we're going to take a general power rule times the derivative of the inside, and that should be our derivative. Now we're going to do a little fancy math here. We're going to simplify a couple pieces, but I'm going to leave a couple pieces alone because I want to factor it. I want you to see the factorization. So hopefully you see what I've done. I've multiplied the 2x times the 2 and this x to make it 4x squared. I've leaving the 48 alone because I want you to see that factorization. It just makes things a little bit easier for us. So I'll be factoring out my 48 from right here. Also, I'll be factoring out x squared minus 16 from here, and one of them from right here. So what that's going to leave us with, be careful on your signs. Check this out. Factor out your 48. Factor out one of your x squared minus 16s. What you're left with is negative x squared minus 16. Negative, and one of those is remaining. Plus, the 48 is gone. We have 4x squared. The x squared minus 16 is gone. Check it with distribution if you really want to, but if you distribute this in, that's negative 48 x squared minus 16 squared, plus 48 times 4x squared, and then x squared minus 16. So that's the correct factorization. Almost done. One last little step. What we're going to do is simplify this a little bit. If you look at that, that's negative x squared plus 16 plus 4x squared. That's 3x squared plus 16. Also, we're going to simplify out one factor of x squared minus 16. So gone, part of that's gone. That's our second derivative. That's about as good as we can make it. Now, what the second derivative is, again, it's concavity. It's how your slope is changing, or in other words, the curvature of your line, of your graph, if you will. So whether it's increasing or decreasing, we can have two different types of that. We can have increasing concave up, increasing concave down. We can have decreasing concave up. We can have decreasing concave down. Just like that. So what this says is to find those points where you change, where you possibly can change concavity, set your numerator equal to 0 and your denominator equal to 0. The numerator gives you the possible inflection points, like the actual numbers, the values, where you can plug them into the actual function and get a point. The denominator says where the second derivative is undefined. Well, it could still change concavity at those places, but you probably won't find a point because it's most likely an asymptote. So here, if you try this, well, notice that. 3x squared plus 16. Is that ever going to work for you? 3x squared plus 16 equals 0. Well, 3x squared equals negative 16. X squared equals negative 16 over 3. Can you have x squared equals negative? The answer is no, not the real number system. So here that's not going to give us any possible inflection points. So the numerator pretty much doesn't give us anything. The denominator, you're going to see again, those same points keep popping up. Even from the beginning of our function, we had 4 and negative 4 as being undefined. That happens here as well. So again, we're going to have the points 4 and negative 4. Okay, again, take a close look. That's our second derivative all worked out for you, nice and pretty. Set equal to 0, numerator, nothing. Denominator, same points we've gotten before. I'm going to erase it, and then we're going to talk about step number 5. We'll plug all this stuff in, we'll make a nice table, we'll have the points from our original function in step number 6, and then I'll graph it. And what this gave us was 4 and negative 4 again. Now, when we make the table, hopefully you remember this from class or from previous videos if you're watching this on video. We put our first derivative up top, second derivative on the bottom, and basically it gives us a kind of a concise version of our graph, of our function on a graph. So we're going to put all of these points on the top, gotta be in order. And these points on the bottom. And what we do is we test specific points in each interval, and what that's going to tell us is where our graph is increasing or decreasing for the top, that's our first derivative, or concavity for our second derivative. So I would test the points like -5, -1, 1, and 5. And we're testing them in the respective derivatives. So here, we'll be using the first derivative. On the bottom, we're taking second derivative, so concavity, and we'll test some similar points, but make sure you put them in the second derivative, not the first, not the original. Original function gives you points on a graph. First derivative gives you increasing or decreasing, second derivative gives you concavity. So let's try this. If you want to try it at home, plug in your own points. But we're going to try f prime of -5. That's a negative times a negative. This is our first derivative. Again, remember, first derivative. Negative times a negative is a positive. That's a positive because it's squared. That means that this is positive. You don't exactly care about the whole value of it. You care whether it's positive or negative. Increasing. -1. Well, that says negative times negative is a positive over a positive. Again, that is positive. Increasing. Next up, we have 1. Negative times a positive is a negative over a positive. That's going to be a negative. Decreasing. 5. Negative times a positive is a negative over a positive is still a negative. Decreasing. Second derivative is telling us some more things. It'll say plug in -5, but now do it to the second derivative. Second derivative is right here. This is, well, let's see. -5 squared, well, it's going to be positive, plus positive, positive, oh, that's positive.
I'm not paying attention. Oh my goodness. This is boring. No offense, Professor Leonard, of course.
Oh, you know what? I made a mistake. I think I drew that wrong. If you were watching at home, you might have noticed that. What's Mr. Leonard thinking? That should be a power 3. I was
Come on,
kind of thinking through that, thinking, wait a second, that doesn't make too much sense. So let me change it to a positive 3.
Did I write that down?
And then we're gonna check this point again. I think that one's gonna work out for us, but make sure you have a 3 right there, because that would be a big mistake. I forgot to.
True.
I erased it before I copied it down, so bad mistake on my part. Let's check it one more time. Let's check the -5. So -5 squared, that's positive, times a 3 is positive, plus 16 still positive, times 48, that's positive. Now let's check it down here. We have -5 squared, that's 25. Minus 16, well, that's still positive, and when you cube it, it'll still be positive. So we're okay on the concave up. It's still gonna be concave up. This is the one that's gonna be changing for us. If we plug in 0, well, that's 16 times a positive number, that's still positive, but look what happens down here. 0 squared is 0, minus 16, well, that's a negative. What happens when you cube a negative? Well, it's still a negative. So this is gonna be concave down. And it's concave down for its entirety. Notice how we didn't get that 0 in our second derivative, so that's not going to be a place where we're changing concavity. 5, same thing's going to happen as -5. We're going to have a positive up here, we're going to have a positive down there. That's concave up. Well, that takes care of step number 5 for us. So far we've found our x-intercepts, our y-intercepts. We've gone ahead and done our first derivative and our second derivative. We made up our table. We have all of our intervals of increasing. We have decreasing. We've got concavity up there. We're almost done. What we need to do right now is find out some points, what our points are, plot them on our graph, and look at how this is going to be graphed for us. So, points. Well, our points are already on the board. We have our x-intercepts, we have our y-intercepts, and we have our asymptotes. You're going to notice that all those points come back again at us. We have 0. Well, if we plug in 0, you get 1/2. That was our y-intercept. So all of our points are basically listed. We've got 2, 0, -2, 0. Those are our x-intercepts. We've got 0, 1/2. Keep in mind what that is, though. That's our y-intercept, and it's also, if you look at it, it's also this, which is increasing to decreasing, increasing to decreasing. That's a relative max. Relative max. Is there a relative min? No. This says increasing, increasing, decreasing, decreasing. There's no way we're having a relative min here. Doesn't happen.
True.
Also, inflection points. We could try for inflection points. We could try for some of these points, but you'll see when you plug them into your original function,
Like this, right?
you've got 4 squared minus 16. You've got -4 squared minus 16. That's undefined. That's how we got those asymptotes in the first place. So
Or is
these
it like-
things are all asymptotes. What it means is we only have 3 points to graph.
No, this is increasing, but it's decreasing
Now,
here, so it'd be like.
I told you in class or on the video that a lot of times you can actually graph these graphs just by looking at the asymptotes and increasing, decreasing. I'm going to try to show you that right here so that you can kind of visualize what it's going to be even without the second derivative sometimes. So if that's what you're looking for, this is the part that you want. So, number 1, do your asymptotes. Asymptotes are vertical 4, -4. Hopefully you're okay with our asymptotes. Horizontal says 2 in each direction. Now, keep in mind, horizontal asymptotes only work as you're going to infinities. So, could you cross it here? You could. It doesn't mean it's like a wall for you. Well, it's a wall for the y. Yeah, for our vertical. But horizontal, not necessarily. So horizontal says 2 in both directions. But it only starts out here. The next thing you do after you take care of your asymptotes in your graph, you're going to plot all of your intercepts. So our intercept says 2, 0, -2, 0, and 0, 1/2. We're going to label what they are too. I've showed you that when you label it says 2 in both directions, but it only starts out here. The next thing you do after you take care of your asymptotes on your graph, you're going to plot all of your intercepts. So our intercept says 2, 0, negative 2, 0, and 0, 1/2. We're going to label what they are too. I've showed you that when you label these points, well, they're intercepts, those don't do much for us besides say you cross the x-axis here. But that said, you have to be a relative max. That's what that said. We listed it as. Now, just think about it. Even if you don't have a second derivative, so let's just pretend I didn't even do the second derivative. What's the only way we could fit this information on this graph with just the first derivative? So hint, hint on that test. If you're looking at how do I do the graph with just the first derivative, sometimes you can do it. This is one of those cases. Sometimes you can't. You need the second derivative. But a lot of times, if you have asymptotes and you have increasing, decreasing, you can picture what this graph looks like. Here's what I'm expecting from you. If you know that your asymptote goes this way and this way, there's only 2 scenarios. You're either going, and you don't have any relative max or min. Notice you don't have any of those in this interval. You don't have any of those in this interval. You do have one in this interval. But other than that, there's no change in increasing. There's no change in decreasing. So unlike the previous example, we can't do things like this. Otherwise, we'd have a relative max. We can't do things like this. Otherwise, we'd have a relative min. It's either going to be up or down. That's it. It's the only thing we can have. So when you look at it, if there's no relative maxes or mins, there's no change in increasing, decreasing, look at the first 2 intervals. It says you are increasing all the way to 0. You're increasing all the way. So from, actually to -4, that's where we're really looking. From -infinity to -4, you're increasing. Can this be increasing? No, that would be decreasing. Increasing says this way.
Wait, it's gonna
So
look.
to fit this on a graph, if you have a horizontal asymptote and a vertical asymptote, that's the only way it can be. That's it.
Hold on. Still like this?
Now, what about this section?
Yeah, this is right.
This section says you're increasing from -4 to 0, you're increasing from -4 to 0, and then you're decreasing from 0 to 4. Well, what's the only way that you can increase and then decrease and have one relative maximum and touch these 2 points? The only way it could possibly look is going up and coming down. That's it. I'll talk about concavity in a minute. Just want you to see the idea of fitting your graph to asymptotes first. Now, after +4, it says you're decreasing. Decreasing, mind you. Like this? No, that would be increasing. Like this? Yes, that is decreasing. There's no relative max, no relative min. That means you're decreasing throughout. It means you have to go from left to right, downward. The only way you're going to fit this asymptote and this asymptote is with a picture like that. Now, I have gone ahead and done the second derivative for you, and I gave you the table as well. If you want to go that far, that's fine. In fact, most times you really should. I'm just trying to get you to think outside the box here. But if you compare the concavity with this, let's see if it works. It says you're increasing and you're concave up, all the way from -infinity to -4. Increasing and concave up looks like this. That's what we have. Increasing, concave up. Then on this interval, from -4 to 0, that's here, it says you're increasing, but you're concave down. Well, look at that. If you have these asymptotes, increasing, concave down, that's exactly what we did, and we fit it to our points, -2, 0, and 0, 1/2. We had to do that. From 0 to 4, you're decreasing and you're concave down. Decreasing, concave down looks like this. So from here, we're decreasing 0 to 4 and concave down. Hey, that works. Last section. From 4 onwards, we're decreasing and we're concave up. Decreasing, concave up looks like that. Decreasing, concave, we got it. That's our graph do all 7 steps, you have your picture. But sometimes with these rational functions, if you have those asymptotes handy, you can sometimes take your first derivative and just look at that graph and put it in the right places, and the concavity does work out for you.
Awesome.
We are going to tackle how to maximize and or minimize some functions, specifically some continuous functions. So basically, if we're maximizing or minimizing continuous functions, we have really 2 scenarios. We're going to talk about them over closed intervals. Closed intervals, closed finite intervals, or open infinite intervals. So basically, it asks this. If I give you a continuous function, will it have an absolute maximum? Will it have an absolute minimum? And how can you apply that to real life? We're talking about cost. If you're a business, you probably want to find out the lowest cost, right? Or you want to find out the maximum profit. That's probably what you want to do, right? You want to find the maximum cost and the minimum profit. That would suck, because then you're going to waste a lot of money and you're going to get fired probably. Or if you just guess, you're not going to be making as much money. You're going to be spending too much money if you just guess at things. I think if we produce this amount, then it's going to be good. Let's try it. Well, why don't you do the calculus and figure out exactly what you need to produce, exactly how much it's going to cost, and minimize the cost, maximize the profit, and that's pretty much the idea. Does that make sense? If you're making stuff, you want and you're trying to, like, boxes, are you going to make a storage box that's this long and this wide and that deep? Would that be a good storage box? Not if you want to maximize the volume, right? With the same amount of surface space. So if I say, here's 1,000 square feet of cardboard, make it the best box you can. We should be able to do that. We should be able to figure out the dimensions using some calculus. And that's what we're talking about, maximization problems. Well, I'm going to relate this back to absolute max and absolute min. Here's the idea. If you have a closed interval looks like this with brackets. If you have a closed interval with brackets, do you for certain have an absolute max?
Yes.
Absolutely. Do you have an absolute min? So for a closed interval, because these have brackets, you will certainly have solutions. There will be solutions. If it's a continuous function and there's a closed interval, always. How about open? Open intervals. Because remember with the absolute max and absolute min, if you think back, if you watched the video from a while back, absolute maxima and minima must occur at one of 2 places. Must occur at relative max or min for continuous functions, relative max or min, or at endpoints. Do you remember talking about that? If I take away the fact that it has endpoints, well then it must occur at relative maxes or mins, which don't have to be, could be, but don't have to be the absolute max and min. So while a closed interval will definitely have an absolute max or min, or will definitely have a maximum and a minimum, because we have endpoints, this one might not have them, because there's no endpoints. Are you with me on this? So it might not have solutions. Well, we're going to jump right into it with an example. We'll start off quite simply. I want to basically do this example to give you some vocabulary and how to do the problem. Let's say that I want you to build a region that's fenced in. So basically a rectangular region. So basically Wyoming or something. I think it's pretty much a rectangle, right? Well, if you consider the Earth to be flat, it would be a rectangle. It's curved. Well, never mind. It's a surface space. But let's pretend the world's flat for Wyoming, because have you been to Wyoming? It pretty much is. Not really, they have mountains and stuff. But let's just pretend it's flat and it's a rectangle. I want you to fence it. We're going to make this easier than that. But basically, you're fencing a rectangular region. Yeah.
And they only have
Fence a rectangular region and maximize the area. You have 100 feet of fencing available. Of course, this is not Wyoming anymore, okay? But because Wyoming is very large, we're just going to fence some regular area, okay? And you have 100 feet of fence. This, by the way, is called something specific for these applied problems. It's called a constraint. It says this is what you have to work with. It's putting a limit on your area, basically. Because if I said maximize the area, you just go, okay, I'm going to make it as long as I can times as wide as I can. That's maximizing. But if as soon as I say, oh, you only have 100 feet of fencing, well, that changes things, doesn't it? You have to have that statement. That's called a constraint.
Got it.
Constraints can be given to you. They can be implied in the problem. They can be realistic constraints. But somewhere in most of these problems, you will have some sort of a constraint. Now, one great thing to do with these applied problems, they're all going to have something you can draw. So try to draw a picture of them to get your mind wrapped around it. We're talking about a rectangle here. So
this is an
we're
introduction
probably
to
going to want to draw
integrals.
a rectangle here. So let's draw a rectangle here. Doesn't matter what you call the sides, but call them something. Call this one maybe X and this one Y. Bless you. You with me still? What's this side? Good. And this one's Y because inherently we know about rectangles. Opposing sides are of equal value. So we have that. The next thing you do, you come up with some sort of area that has to deal with what you're trying to maximize or minimize. Something you're trying to find the maximum or minimum of. Very much like with related rates, right? You're trying to find an area that incorporates everything. Here you're trying to find a formula that incorporates everything. Here you're trying to find a formula that incorporates what you're trying to maximize with your figure. So we want our formula. And you need to list out any constraints that you have. Okay, tell me something. We've already drawn our picture. Let's come up with a formula that has to do with what we're trying to maximize. What are we trying to maximize here,
X
ladies and
times
gentlemen?
Y equals 100.
Okay, so if we're trying to maximize area, you need to be able to come with a formula for the area. What's the formula for area?
100.
Specifically for this, what's the formula for our
X times
area? XY would give us the area of that rectangle. True? X times Y. Now let's talk about our constraint. What does the 100 feet of fence have to do with anything?
It's the maximum.
What's that called?
The domain of the function.
Oh, kind of, sort of. Perimeter. We'll talk about domain in a minute, okay? But the 100 feet of fencing, you know that goes around your figure, right? So that is your perimeter. So right here, our formula we're trying to maximize is the area. You with me on that? That's what the question says. But a formula that's inherent in our problem has to do with our constraint. And it says, well, I know that if I add up all the sides, it has to equal how much? Now, add up all the sides. How much do you get? Good, if I add that up, I add this one, this one, this one, this one, that's 2 x's plus 2 y's. And you get another formula out of your constraint. Raise your hand if you feel okay with this so far. Okay, very good. Now, the question is, what are we trying, here's where you answer your question if you have two more than one formula. What are you trying to do here? Are you trying to maximize your constraint or maximize your area? your area. So what you're going to do, use your constraint, solve for one variable, and substitute it into the formula that you're trying to maximize or minimize. The reason is, can you find a derivative of x and y? Yeah, you can with implicit. However, you're going to need to solve for y anyway to be able to do anything with it. So solve this for y and substitute it in. So we're going to solve our constraint for one variable. I would choose y. Just, I don't know, I like y. So solve for y and then substitute that into your formula. So you're going to solve the constraint. For one variable. And sub into your formula. Okay, you get to choose which one you want to solve it for. I'm going to choose to solve for y. So I'm going to subtract 2x, I'm going to divide by 2, and I'm going to get
50x minus x. Or 50 minus x, yeah.
okay.
50.
So from here,
It's 30.
Really?
yeah, if I divide everything by 2, I'm going to get y equals 50 minus x.
Really solved it.
So far, so good? What that does is says, okay, now that I have y equals 50 minus x, let's take that, let's put it here. That changed our formula from 2 different variables into one variable, and that says I can do something with calculus with it. All right, you need that one variable for us. So I'm going to get a equals x, and instead of y, I need parentheses. Do you see why I need parentheses? Are you sure?
X squared. I had parentheses,
No,
I still
hate
messed
this
up.
wrong. But you need parentheses.
Not
They're
on
important.
top
If
of
you give me
zero.
this, you know I'm
To
going to
be
have a
honest.
cow. Right? Literally, I used to live on a dairy. I could have a cow if I wanted. There's 6,000 of them. You have 6,000 cows. There's only 45 of you. You have 45 cows.
5 cows for each person.
A lot of cows for each person. So far, so good? Make it easier before you do the next thing we're going to do. You see, right now, we have this formula for area, right? What we're trying to do is maximize the area, which is why we're working with the formula for area. Now, what we learned here was that this really is a closed interval. There's only so far I can make my x. I can't make my x or my y like 3,000 feet, right? Because I only have 100 feet to work with. So I'm actually dealing with some domain restraints right there. We'll talk about that in a second. But we know that wherever a maximum or a minimum occurs, it's going to be at either an endpoint, which we'll talk about in a bit, or it's going to be at a relative extreme point, a relative max, like this. How do you find relative maxes? What do you do with functions? That's a function. What do you do with functions to find a relative max? You take a derivative, because you know relative maxes happen where the slope is 0, right? To find the slope, you take a derivative. So with your applied problems, let's take a derivative of that. Now, I wouldn't be so silly as to do a product rule here. I'd probably distribute and get $50x minus x squared and then take a derivative. But we're going to take a derivative because what a derivative is our, what's a derivative again? Slope. And we want to know where the slope equals 0, because where the slope equals 0 gives us a critical point, and that could potentially be our relative max or min. If it's a relative max, that means it could be our absolute max. If it's not, it will certainly occur at an endpoint, but it's something we need to check. So take our first derivative. That would be with respect to x in this case. Notice that if you had solved for x here and plugged in and had y's, you'd have dA dy. You follow me on that? Show your notation appropriately. This is with respect to the variable that you have, x. In our case, you get 50 minus 2x. Are you okay so far? What's that give you again?
Your slope.
Slope, and what do we want to find with the slope? Where it
Equals 0.
0.
If it equals 0 somewhere, that's going to be possibly a change from increasing to decreasing. Might be decreasing to increasing, but it will give us the only point on our interval where that change could possibly occur. That's why we're going to check this with the endpoints later to determine whether it's an actual max, whether it's minimum. How much is x?
123.
Probably add 2x divided by 2.
Yeah, 25.
Probably 25. Hopefully 25.
Not 120. 25 something. I got the 25 right.
We will feel okay getting x equals 25. Now, if x is 25, how much is y? Use your constraint to solve for that. Just plug in the 25. Y's gotta be 25. So if x is 25, we use this again. But then you're gonna have to check. See, here's what we did. What we did is we found out that the only possible place where we have an absolute maximum other than the endpoints is right there. Would you agree with that? That's the only place that we change from increasing to decreasing or decreasing to increasing. That's the only relative, even possible relative extreme that we have. And what we know from before is that absolute max, which is what we're trying to do, max or min, absolute max must occur at endpoints or at relative extrema. Our endpoints are, well, we'll talk about that. We're going to check right here. But our possible relative extrema is at x 25. Although there are some endpoints here. Can you tell me what's the biggest thing we could make x? Wait, 100? If you did 100, you'd have a one-sided fence. Not 99.
75.
Oh, no, too big still. 50. X could be 50. You have two x's, right? So if x is one thing, it has to be the other thing on the other side. If you do 75, you can't do 75, 25. That doesn't make sense. It's not a rectangle. Now, you might be thinking, well, is 50 and 50 a rectangle? Technically, yes, kind of. If you have 50 and 50, how much is y going to be? That's going to be a rectangle. Is that going to maximize your area? Actually, has 0 area because it's 50 times 0, right? That would be 0. It'd be a line. You get just a fence next to a fence. But you could do it, right? So the maximum that x could be. Like, you are the stupid. You may be.
It's for skinny cows.
Skinny cows come from California. Okay. So x is 50 equals the maximum value you can make x because 50 plus 50 equals 100. What's the least value you could make x? 0. Because then y would be 50 and 50. Right? That'd be a straight line in the other direction. Again, your area would not be good. But here's the point. Okay? This is kind of a simplistic example, but it says this. It says if a maximum is going to occur, it occurs here, here, or here. It has to occur because this is a closed interval. It's going to be here, here, or here. So x is bound between, here's our endpoints. This says x is somewhere in the interval, that's what that little element says, somewhere in the interval of 0 to 50 inclusively. Including 0, including 50. That's somewhere where x is. If we have this interval, which is our inherent constraint in our problem, then our absolute max must be one of these three numbers. We know it's either endpoints or it's at a relative extrema. And that's the only place we could possibly have a relative extrema. Nudge if you feel okay with that so far. All right. So, you're going to plug them in. Where are you going to plug those in? First derivative is going to give you 0, because that's how you found that number. It's not the first derivative. What gives you values, people? The original function. In our case, that's our original function. Or if you have the y, you can plug it in there. That's okay. But plug it into here, and that's going to maybe be a little bit easier to do, I would say, for just x's. If you plug in 50, check it out.
0.
What's 50 minus 50? Your area is 0. We talked about that. That's a straight line this way, right? Plug in 0. 50 minus 0 is 50 times
0.
gives you, that's the y equals 50 and 50. That would give, that's minimizing your area right there, 0 and 0. This one hopefully is maximizing, hopefully it gives us something. Plug in 25. This said the area is 0. This said the area is 0. This said the area is we knew it had to be one of those three. This is the biggest one, ergo it must be your absolute maximum. So what do we say? The absolute maximum is 625 square feet when x equals 25. Basically, what shape do you have? You have square.
And then you just plug it into the constraint.
25,
Right?
25, 25, 25, because
And
that
you
x
get your
and
y
y are
value.
both 25. So how you'd write it out, I really don't want to erase any of this, but I'll write it down here. The maximum area is 625 square feet, be specific. When x equals 25 and y equals 25. Feet. Do you feel okay with our example? Yes, no? We're gonna go a little bit quicker now. We're gonna, because we understand the idea, formula, constraint, put them together. That's basically the idea. Let's talk about one that we've actually had before. If you want to go back and refresh your memory on the video, we had this problem, excuse me, this problem, but we didn't do anything with it. Do you remember the problem where I said, I want you to take a piece of cardboard I want you to cut sections out of it. I want you to make a box. Oh, it came out better this time. A lot better. Do you see the box? Good, I did my job. If I make this, what would I say, 16 and 30? Doesn't matter, let's do 16 and 30. This is 16 inches. This is 30 inches, and each of these cuts is X. So the problem from a long time ago was, let's suppose I had this box of
Cardboard
this piece
box,
of
yeah.
cardboard, and I cut X's, squares of X in each corner. I could fold up the sides, and it would make a box like that, right? An open box like that. Do you remember that problem? Do you recall if this is this side, and it's not to scale, of course, but if this is this side, what's the length of that? Is it still 30? 30 minus x is close, but it's not 30 minus x.
30 minus 2x.
30 minus 2x, yes, because you have an x from each side. You okay with that? Follow? How much is
16 minus
that
2x.
side? Is it still 16? Very good. Okay. How much is the height of our box? Whatever the size of the corners you cut out, that's going to give you the height. Do you follow? You're taking this square, right? You're cutting out a square. You're going to fold up this side, fold up this side. It's going to give you that box. It's going to be a height of x. Show of hands, how many feel okay with our picture? Now, what we want to do in this problem, I want us to find out the maximum volume that we can make this box. So let's say you're working for UPS, right? They say we get so much of this stuff. We have so many pieces of cardboard left over. They're 16 by 30. I want you to take a stamping machine, cut out X's, fold them up, take the sides. How many boxes can we make? Or sorry, what's the biggest size of box we can make out of this? And you go, well, I don't want to just waste product. Let me do the problem real quick. So let's figure this out. So we want to maximize the volume. Well, I told you there's really two things we do after we draw a picture. Number one, we draw a picture. Number two, we got to
The
find
formula
a
and the
formula.
constraint.
We got to find any constraints that we have. So let's work on a formula.
What the? Oh, spoilers.
Number two, we got to find a formula. We got to find any constraints that we have. So let's work on a formula. Can you find a formula for volume? Because that's what we're trying to maximize. Say it again. So basically all three dimensions times each other, right? In our case, can you tell me more specifically what that will be for us?
30 minus 2x in parentheses.
Oh. That's important. Yeah, you should have that. And then what else?
16 minus 2x times x. Times x.
I'll put the x out front. Is that okay with you? So don't forget about it. One dimension, length times width times height was going to give you the volume. You feel okay with the volume? Now let's look at a constraint. It told you nothing else about this problem. It just said, I have this, make me a box. I told you nothing else. However, inherently in this problem, there is a constraint. In fact, we talked about it the first time we had this. If you watch the video, you can see it. There's a constraint here.
X can equal
What's the
0.
constraint?
Size of the cardboard.
Wait, why not 16? Why can't x be smaller than 16? Why is it 8?
Because you have to take it from the side.
Very good. If you didn't hear her, she said you have to take it from both sides, right? So if I make an x cut here, I have to be able to make the same x cut here, right? If I go more than 8, I've overlapped, I don't have any more stuff to cut off. So 8 is the maximum cut I can make. Would it be a good idea to cut off 8? If I cut 8 and 8 and 8 and 8, that's gonna be the worst box ever. It's gonna be a really small piece of cardboard, and you go, hee hee hee, and they're gonna go, dude, seriously, you're fired, right? That would be silly, you don't wanna do that. So, you could do 8, you could, but you know it has to be less than that or equal to 8. What's the smallest cut you could make? What if you didn't make one? You'd have the second worst box ever, right? The first worst box is you cut something off and you fail to make a box. That's the 8 and 8. You cut off 8, you cut off 8, that's gone. You cut off 8, you cut off 8, that's gone. You basically have a 14-inch by, whatever that is, 14 by 16 flat piece of cardboard. If you don't make a cut, at least you have a 16 by 30 flat piece of cardboard, but it's still not going to hold anything. But you could check it. Understand that that is my inherent constraint. Do you see it? Okay. We have a formula. It's in terms of one variable, that's great. If we had 2 variables, we would need another constraint to work with it. We have a constraint that's going to limit our end results, that we're going to check our endpoints there. What do you do now? You're trying to maximize, right? You know maxima and minima have to occur here, here, or somewhere in there, right? It's got to be in there. But the places where it occurs are the places where the slope is going to be 0, right? How do you find the slope? Take a derivative. When all else fails, take a derivative. You gonna take a derivative of this product rule? No, you're not gonna do that. Why don't you distribute it out, see what you get, take a derivative, set it equal to 0.
I don't know. I don't feel like doing that. So we'll see what Professor
So that's volume.
Leonard gets.
I don't know if I did that right. Did I do that right? Did I mess it up?
Sure.
I did right?
Oh, sweet.
Seriously?
Really?
Good, because I was guessing. I was totally guessing.
Yeah, no, you did.
No, I'm just kidding. I knew it. Anyway, so you distribute it, you combine everything together. Hopefully you got that far. Did you get that far? Now take your first derivative. Make sure I'm right, by the way.
Set equal to 0.
I like
find
being
the
right. That's awesome.
critical points.
Sorry, that's v of x. So v prime of x is that. Just no? Okay, that's nasty. What do you do with that? Set equals 0 and pray you can factor out 12. Right? Set equals 0 because that's going to give you the only places where you have a critical point. Critical point is the only place you give a relative max, relative min. So set this thing equal to 0.
Wait, what? Oh, he didn't find that. Okay. I thought he found the derivative already. I didn't know that was just foiling it out.
Does 12 factor out of it?
No?
What do you do? Try 6. Does 6 factor out of it?
No, you can do 4.
Do you do 4? You can't do 6? Darn it. Hate that. You can do 4? So 4 factors out of it. You can still factor out the 4 though, right? If you don't want to do quadratic formula, that's How much is that divided by 4?
46.
120?
Mhm.
Well, you can try to factor it or use quadratic formula. Do you remember the quadratic formula?
Yeah, 9
X equals, what? Oh, we should watch Matt C video. We even sing about it.
minus 8.
X equals minus b plus or minus radical b squared minus 4ac all divided by 2a. Get it?
That brings back so many memories of high school. First time I've ever heard that song.
Really?
Yeah. I love that song.
Wait, what are we doing?
Memories of high school.
B squared minus 4ac all divided by
No, quadratic formula.
2a. Get it? 4ac all minus b. Matt C video. We even sing about it.
Minus 8.
X equals minus b plus or minus radical b squared minus 4ac all divided by 2a. Get it?
That brings back so many memories of high school. First time I've ever heard that song.
Really?
Yeah. I love that song.
Are you working it out? Have you already worked it out?
I don't know what the right answer is.
I have no idea. Those are too big for me to do in my head. I don't know. I don't know what it is. I'm gonna
23 plus or minus 2.
total.
Oh, no, just wrap, not even.
This is
21.
2116 total.
No, 76.
Total
676.
766. Oh, damn it. 676.
6. That's easy.
Yeah.
6. What's the square root of 676?
26.
126.
26.
26. Very good.
And then you get 23 plus or minus 13.
Okay, let's see. You get what?
23 plus or minus 13 over 3.
23.
And then plus or minus 13. You divide everything by 1/2. That's where I did it.
72 over 6
12.
and 20 over 6.
Factor out the 2.
12 and 10/3 is what you're telling me? Yes, no? Yeah. I feel okay with 12 and 10/3. It took way too long. OMG. BFF. TGI Fridays. Tell me something about these points. Why can't it be 12? We can't make an x big as 12. So this one, even though it says 12, you cannot do that. The only one it could possibly be is 10/3. So let's think about this. Now, realistically, we already said, and you can check it, you check your endpoints. In fact, I'll already I'll do it over here. Your endpoints are 0, 8, and the only critical number you had was 10/3. If you make 0 as your x cut, you're going to get a volume of 0. If you make 8 as your x cut, you're going to get a volume of 0. Are you with me still so far? Look at your volume function. It says if you make, let's see, you make a cut of 0, 0 times anything is 0. You make a cut of 8, 16 minus 8 times 2 is 0, that's times 0. So you're going to get a volume of 0. The only one that could possibly work is 10/3. So what you would do, I'm not going to spend the time to do this, but you find out whatever, has anyone done that, the volume for that 10/3? If you do, what you do is you plug in your 10/3, you find your volume, whatever this is your maximum. So the maximum volume would be plug in 10/3 to your original volume function, figure out what it is. I'm not going to have you do that right now, do it on your own time. Figure out what that volume is, and that will be your maximum volume. It occurs at a cut of 3 1/3 inches. You follow me on that? 3 1/3 inches. How do we feel okay with our maximization so far? You ready to try something a little bit more fun? Because when are you ever going to do this in real life? Well, maybe. Yeah, I'm not a box cutter. But I do build oil pipelines in the middle of the ocean, so let's do an example like that, okay?
Wait, really?
No, I wish.
That's a summer job.
Seriously though, any questions just before I erase it? Do you understand the idea? You understand how to draw a picture, come up with a formula that relates that picture to what you're trying to maximize or minimize? Do your derivative. It's all about the derivative. Set equal to 0, solve it, come up with your constraint, and check your endpoints. That's absolute max min. That's exactly what we've done before in, what, 3 point, I don't know what it was. We've already done that. You said you plug in your endpoints, you plug in any critical numbers you had, whichever the biggest one, max. Smallest one, min. No problem. That's the idea.
726.
How much?
726.
726? Anybody else get the same answer?
I did.
726. This would be in cubic inches.
Awesome.
You guys ever go to Santa Barbara? Ever? You ever see those oil pipelines out there? Sometimes they have pipe, let's say you want to build one of those, but you wanted to not have tankers go back and forth. So what you're going to do is build that thing and then build an under the water pipeline to land, because you have a refinery right off the coast somewhere. So here's what happened. Your refinery's here at point B. The oil you located is there. Oil. If you were to go directly from the oil to shore, we'll call that point A. Here's the idea. Here's what you know about the situation. Pipe costs a whole bunch more to put it in the ocean than it does on land. You gotta have people go out there, lay it right, go under the water, put the pipe together, do all this stuff, okay? Now we're gonna make this kind of simplified. It probably doesn't cost a dollar per kilometer, but we're gonna say it costs $1. Maybe it's like $1 million per kilometer, or $1 billion, I don't know how much it is. But let's say that it costs twice as much for the underwater stuff as it does for the on-land stuff. You with me on that? So the pipe costs $1 per kilometer in the ocean. And half of that on the land. So whatever it is, you could substitute in different numbers. and you get this right, same exact idea, okay? On land. If we want to minimize the cost, which I hope that you do, right? You don't want to build the worst pipeline for, if you want to build the worst pipeline, you go like this. Let's put the oil way over here, and then down here, and then over here. That'd be stupid, right? We want to come with the most cost-effective way to do this pipeline. So if we want to minimize our cost, what would you do? Would you go like this? Would you make your oil pipeline here and there? Would you do that? I don't know. It seems to me like that would be the least amount of ocean pipeline, but the most possible. It seems to me like here and there. Would you do that? I don't know. It seems to me like that would be the least amount of ocean pipeline, but the most possible land pipeline, wouldn't it? I don't know if that's going to be cost effective. I have no idea. I really don't know. Would you go straight from the oil to the oil stop? You could. That would be the fastest way, right? The least amount of pipe in general. But this is the most expensive pipe you can lay, right? This would be less expensive. So chances are we're going to come to some point that's intermediate that says, well, how can we do this? Maybe we take our oil and we pipe it to some onshore point and then lay the pipe from here to here. Does that make sense? The way, if you label it point P and you say, well, point P very well could end up being at A, right? It could be here, it could be at point B. It'll come out in the formula. It'll be at your endpoints, all right? So let's say, if we want to minimize our costs, how far should point P be from point A? Oh my gosh, I don't know. No idea. Let's try to think through this thing. Oh, there's one more thing I need you to know. Doing your measurements, that's 8 kilometers. Okay, so you know that. And you know that your oil is 5 kilometers off the shore. And those things you know. What we want to know is, where's that point got to be to make this the cheapest? So we're going to basically make it in the ocean pipeline combined with the on the land pipeline and see how far this is. What am I asking here? How far this has to be from there? What do you want to call that? The distance from here to here. Call it some variable, whatever it is. Just call it x. Now let's think critically about this. If this area, this distance is x from A to P, how far is the distance from P to B? Don't use y, because then we have to come up with
How would it be? Oh, 8 minus x, right?
another formula to solve it. Try to base it on x. That's the reason I gave you the 8. X minus 8 or 8 minus x? If this distance is 8, if that was a 2, that would be a 6, right? If that was a 4, that would be a 4. You're taking 8 minus that x. So whatever that is. Okay. Do you feel okay with our picture so far? Do you understand the question? The question is, let's try to minimize our cost if we have to get oil from there to point B. If we know that this is 8 kilometers, we know that it's 5 kilometers off the shore, let's find the best place to do that so that we don't spend a whole heck of a lot more money than we need to. Well, here's the deal. We need to come up with some formula that relates the cost of this to our problem. let's try to do that. Cost. What do you need to know to find the cost of something? Let's see. Well, we need to know how far this pipe is, don't we? Okay. I'll give you the easy one. How far is it from P to B? Ah. Would you agree that 8 minus x in parentheses, would you agree that that is the amount of on-land pipeline we're going to need? Do we need pipe from A to P? No, we're going to go from the ocean to P. We need pipe from P to B. You follow me on that? That's the 8 minus x. 8 minus x. How much is each, and that's in kilometers, 8 kilometers minus x kilometers. How much is each kilometer of pipe on land?
$1.
No, it's not $1. It's a half
Oh,
a
on
dollar.
land.
So would you agree that if
Half
this is the amount
8
of
minus
pipe,
x, right? So it'd be 4x, or
One
4
half of
minus
that.
half x.
remember this is dollars, half a dollar times that amount is going to give us the amount of money it's
Or
going to
x over
cost
2.
to go from P to B. How many people feel okay with that so far? Okay, let's do that. Let's do oil to P. Let's do this distance. How do we do
I'll
that
leave it like
distance? That's a right triangle. That's why, by the way, we call that x. Right, that's why. So that we get a Pythagorean theorem triangle. It's kind of nice. You don't want to do it with 8 minus x. It's crazy. So this is x, that's 5. If this is x and that's 5, this is, I'm going to kind of do it a little quickly for you. This is the square root of x squared plus 5 squared. Do you follow me on that?
Yeah.
Leg squared plus leg squared equals hypotenuse squared. Take the square root of the hypotenuse, and that's the distance from A to P. Oh, sorry, from oil to P. Yes, no? Leg squared plus leg squared is hypotenuse squared. So if our distance is, I'll put it in black so you see it. The square root of x squared plus 25, which, by the way, you can't just take the square root of x squared and the square root of 25, right? That's not just x plus 5. You can't do that. It's square root of x squared plus 25, and you can't do anything with it. Would you agree that this is how far it is from the oil to point P? Okay, so this is the distance from oil to point P. This is the distance from point P to point B. This is all the pipe that we're going to need, right? What's the cost of this pipe? $1. Could you do it with different amounts of money? Of course you could. The numbers get worse. But this is the same idea. How do I have the cost of this and the cost of that? What do I need to put between them?
Yeah, just addition.
No, not parentheses. I need to add those costs. Let's try to think about the formula one time, then we'll start working with this next time. We're going to take our problem and break it down little by little. We're trying to come up with a formula to minimize the thing that I'm asking you for. Here we had to minimize the cost. So to find the cost out, well, you need to know how far your pipe is, multiply that by the cost. If this whole thing is 8 kilometers and A to P is x, then P to B is 8 minus x. That's the distance. Each of those kilometers costs $0.50. That's this portion of it. To get from the oil to point P, which is probably it's going to be some intermediary point, we're going to find the distance using Pythagorean theorem. That's the 5 squared plus x squared. Take a square root of it. That's where we get that. Each of those kilometers costs $1 each. If we have the cost for offshore plus the cost for onshore, that's our total cost. How many feel okay with this so far? All right. We're going to continue working on a problem. I'm going to kind of recap what we did last time, just so you know. So what we're doing is we're drilling for oil off of some coast somewhere, and we know where this oil is, and we know
Did you
where
get a
we want.
haircut?
And so what we're doing is we're drilling for oil. So far, all right. We're going to continue working on a
Big Bird got a
problem. I'm going to
fresh
kind of
cut.
recap what we did last time, just so you know. So what we're doing is we're drilling for oil off of some coast somewhere, and we know where this oil is, and we know where we want the oil to be, and it's not directly out from the shore. And maybe this is too expensive to buy over here, so we got to get the oil from here to our oil stop. Maybe this is our shipping yard, or maybe it's our refinery. We want to pipe it directly to there. You get the idea? So we know one thing about it. We know right now that it's 8 kilometers from A to B. We also knew that the oil happens to be 5 kilometers off the shore. And let me explain the idea once again. What we're trying to do is we're trying to minimize the cost of our pipeline. The pipeline costs $1 at sea. Now, of course, it's going to be more than that in real life, but the principle stays the same. And half a dollar on land. So we had some options here. We could have made the sea line as cheap as possible. That would go directly to the shore, right? But then our land line would be as the longest possible. Maybe that's not going to minimize our cost. We could have gone directly from the oil to our oil stop, which says you don't do any land line, but you have the most expensive sea line you can possibly have, right? So we're saying, what if this is the case? Because we're not quite sure. We don't know what's going to happen. But most likely, we'll have some sea line and we'll have some land line, and that will probably minimize our cost. So we asked the question, how far does point P have to be from point A in order to minimize our cost? That's a whole lot different problem. Well, do we know how far point P has to be from point A
No.
right now? So
Well,
we're gonna
yeah.
call it X. We call it X because we don't know the distance, and if you think about it,
Wouldn't that be... Oh wait, A to P. Okay, I thought he meant from the shoreline to the point.
we're going to have to figure out how far this is, right? That's going to be a Pythagorean theorem problem, which I'm seeing in my head right now. I'm thinking, you know what? I don't want to deal with something very complicated here. Let's just make it an X. So I'm going to pick X. If that's X, and we know the whole distance is 8 kilometers, then the distance from P to B is what? 8 kilometers. Yeah. It says this. It says the distance from, the amount of pipe that we're going to have for our land is going to be 8 minus X. So whatever X is, we subtract that from 8. That's how much pipe we have to have in the land. You follow me on this? But what we also need to know, we've got to know the distance of pipe we're going to lay at sea. So from the oil to point P, we got to know that. And I think I did this last time, but I did it very quickly. We'd use the Pythagorean theorem. It is a right triangle. So it says leg squared plus leg squared equals the hypotenuse squared. If that's true, I'm going to erase my ocean here. Ocean. If we do that, then I know whatever this distance is equal to x squared plus 5 squared. That's a leg squared plus leg squared if I take a square root of it. The reason why I got to take a square root, the hypotenuse squared equals that. So to get the hypotenuse, take a square root of both sides. So our distance here is the square root of x squared plus, let's just change it to 25. You okay with this so far? Now, before we work on the formula, I don't think I did this last time. Let's talk about a constraint. Let's talk about a constraint on x. What's the least amount of distance you could have for x? Remember, x is the distance from A to P. What's the least amount you could have? You probably wouldn't want negative, right? If you did negative, you'd go this way. Would you want to go this way? That'd be pretty stupid. Because you go, let's make our oil over here and then run it. That'd be really silly, right? We'd probably go this way. That way it's closer to our oil. So 0 is the least amount we could make x. We could go directly from oil to shore, right? 90 degree, directly right there. That'd be the shortest. That'd be probably the best way to go if that minimizes our cost. We're not going to go this way. We go straight down. So 0 is the least we could have for x. But it could be 0. What's the greatest we could have for x? Yeah, you're not going to do this. You're going to go, ooh, let's go way fast and then come back. Well, that'd be pretty stupid as well, right? You'd maximize costs, probably, well, maximize costs, you go everywhere. But you go way past and then come back, that'd be silly. So we could have 8. You'll agree that x has a minimum of 0 and a maximum of 8. Well, what that does for us, that gives us some inherent constraints, that gives us some endpoints. What this says right here is that if we have endpoints, which we do, 0 and 8, and we find a critical number, one of those points is going to minimize our cost for us. It's either going to be at 0, 8, or somewhere in between there if a critical number exists. Do you follow? Okay, so at least we have our constraints down. Now let's talk about the formula. Here's how you come up with a formula for the cost. I didn't start with this last time, but I'd like to show this to you. To find out your cost, you really just have to identify the pieces of your puzzle, the pieces of your picture in this case. You go, all right, I know you have some pipe at C, so the cost of the pipe at C plus the cost of the pipe on land. Well, since we know how much it costs per kilometer, let's just figure out the kilometers. So the pipe on the land. We just talked about this, but the pipe on the land is from P to B. That's our 8 minus x. So if we know that the distance of pipe is 8 minus x, and it costs $0.50 per kilometer, this is how many kilometers we're going to have of land pipe. We're just going to take half of that. That's going to be the number of dollars we're going to spend for the pipe on the land. You okay with this so far? That's going to be added to the pipe at C. Now we just figured out how much pipe we have at C. It's a square root of x squared plus 25. That's how many kilometers of pipe we're going to have under the sea or at the sea, in the sea. Each of those kilometers costs $1. So if I multiply $1 times each of those kilometers, I'll have the total cost for the pipe at sea. And that's how you figure out the cost function in terms of x, the distance that you're looking for. Raise your hand if you feel okay with that so far. I think that's where we actually left off last time. Now, what do you want to do? What do you want to do with this? Maybe before we take the derivative, make it look a little bit better, right? Probably distribute that half into that 8 minus x, because you don't want to start dealing with derivatives until it looks kind of pretty. Deal with that 1 out front, that looks nasty, so, or it does not do anything, but it looks silly. 1 times anything is anything, so the square root of x squared plus 25. Plus, this is going to give you 4 minus x over 2, or 1/2 x if you prefer.
Can you not do
Still
this
okay
with the
so
square
far?
root?
Now, that's our cost.
Huh. Maybe because it's addition, it's not being multiplied together? I don't know. Oh, he writes it as half x.
Cost function. And that's what we're trying to minimize. Maybe do one more thing with that square root. What would you change the square root into? To the 1/2. Not negative 1/2, right? Not negative 2, but to the 1/2. If that's the function we're trying to minimize, here's what you know about maxima and minima. Absolute value, or I'm sorry, absolute maximum, absolute minimum. You know that they occur at endpoints or critical numbers. We know that for a fact, right? It's the only thing that happens with continuous functions, and that's continuous on the interval. So it's either going to be at endpoints or critical numbers. We have our endpoints, which we'll check in a while. We don't have critical numbers. How do you find critical numbers? That's where the calculus comes in for max.
If you distributed this exponent, it's going to be x plus 5, so I don't know why he still has
It's
it.
never minimizing things. It says you find out what the critical numbers are. Those are the only.
Maybe because this is something about the original function. I don't know.
Places besides endpoints where you could possibly have an absolute max or an absolute min in our case. Do you follow me? Go ahead and take the first derivative there. What type of rule do you need to apply to take the first derivative here?
That's okay. Maybe that's why. But wouldn't it be easier if you just distributed the exponent and then took to the derivative?
General problem. Okay. Did you get that far? What key piece of information have I left out so far?
The exponent.
Exponent. Don't forget the exponent. You're subtracting 1, right? You're not subtracting 1 half,
Oh,
you're subtracting
true.
1. So if we take 1 half minus 1, I need to be getting that negative 1 half. Did you
I
get that
forgot
as well?
that actually.
Okay. Then derivative of the inside, we know that because that is a
Oh,
general
so you
power
can't
rule.
distribute it.
How about the 4?
0.
How about this?
Negative 1 half.
Oh, good, okay. So not another product rule or anything crazy, you just take the derivative of that little piece, that's negative 1 half. Now, this is going to equal 1 half x squared plus 25 to the negative 1 half times the derivative
2x.
minus 1 half. Now, I know I get crazy on you guys about parentheses. I know I do. Should you have parentheses around this? No.
No.
If this had all been in parentheses, then yes, you would have, but you don't. This is minus 1 half at the very end. Do you follow me on that? In this case, that says that this 1 half and this 2, that is something that you can simplify out. Does that make sense? I'll show you in 2 steps. This will be 2x over 2 square root of x squared plus 25, true statement, minus 1 half. Yes, no? And then the 2's are gone. So the first derivative of our cost function, which we're trying to minimize in this case, is x squared plus 25 square root minus 1 half. That looks fairly nasty enough. What are you supposed to do with that thing? That's our first derivative. What does the first derivative stand for? Slope, okay. What do we do with that?
Equal to 0.
Can you explain why? I know we've talked about a lot. Can you explain why we have to set our first derivative equal to 0?
The slope's
Why
equal to
do we do
0.
that?
Your maximum
Get a
is
maximum.
going to be wherever the slope is 0.
Very good. So we know that maximum, absolute, what he said was absolute maximum, absolute minimum have to be at one of a couple places. First, endpoints could happen. But if they don't happen at endpoints, they will happen where we change from
Slope is 0.
increasing to decreasing or decreasing to increasing. In either case, the slope will be 0 at that point. So if we set our slope equal to 0, that will solve for the only points where we could possibly change from going up to going down or going down to going up. Does that make sense? That's why we set it equal to 0. So let's do that. Oh goodness. What now? Cry. Give up. Go on spring break. Let's just leave. No, seriously, what do you do? No conjugate. Probably add 1 half.
Oh, is that all? Should be alright.
Why add 1 half? Well, you actually have something nice here. Kind of nice. A little bit nice. Not super nice, but a little bit nice. Do you see what you have here? You have a fraction equal to a fraction, right? That's called a... Starts with a P, rhymes with or portion. Proportion. Yeah, proportion. What do you do with proportions? Oh, dear me, yeah, you cross multiply. That's fine, that's great. Cross multiply 'em. Go.
Is that easier?
You're gonna have 2x equals 1 times the square root of 25, x squared plus 25.
It's like harder.
That looks a lot better. Why does it look a lot better? You already have a square root isolated. Get rid of a square root, how do you do it?
Square.
Square both sides. So let's square both sides. Don't forget that when you square both sides, you're not just squaring the x, you're squaring the 2x.
Maybe he doesn't want it to be a fraction. Interesting.
You follow me? Square, square, gone. 4x squared equals x squared plus 25. Nothing changes. No distribution. X squared, the square and the square root, those are gone. They're inverse they're inverse exponents. In fact, if you think about it, it's actually 1/2 to the second power, right? You multiply exponents and they're being raised to each other.
Right.
That means 2 times 1/2 is 1. So it just disappears. It's great. What now? Solve for x. So I would probably subtract the x squared from both sides.
I see why I did that now. He wants to actually like isolate the variable.
Since there's not an x term, this is nicer. This is 3x squared equals 25. You with me? There's no nasty factoring to be done, nothing like that. Get rid of the 3. How do you get rid of the 3? When there's not an x term, this is the way you deal with quadratic. You just solve it for the x squared and take a square root of both sides. If there was an x term, you'd have to use quadratic formula, or you'd have to factor it, or complete the square. But when there's no x term, no just x to the first power term, this is nice. Divide by 3, you get x squared equals 25 over 3. Get rid of the square. Sorry, what does that again? So square root both sides. What do you need when you square root both sides? Yeah, you have to show that. So you get the square root of 25 over 3, plus or minus, of course. That's going to be plus or minus 5 over root 3. If you rationalize, multiply by root 3 over root 3, you know what rationalization is, right? You're going to get 5 root 3 over 3.
I forgot you have to do that.
Tell me something about one of these numbers.
The negative is
Say again, why is the negative not an answer?
It's not much.
It's not in there. It's not in there at all. This is actually negative. That would be this case. That'd be going this way. We don't want to go that way. Okay? So we're not going to take the negative. So our only critical number (5 root 3 over 3). Now, do you automatically know that that's going to minimize our cost? Not really. You do have to check it. Okay, so what if we did this derivative and that actually was not this? It could very well be this, couldn't it? What if we did that? We would have just maximized our cost. Now, intuitively, we probably think that this is going to be a minimum because we're kind of thinking, this is really expensive. This is the longest distance, so it's probably somewhere in between there, but you have to check. I mean, people have made some serious mistakes by taking a derivative and not checking whether it had the minimum or the maximum. With simple formulas like this, you can think about it. But advanced formulas, oh man, you got to check. The way you check is either with a second derivative, right? Either that, and that would test concavity for you and say, oh, okay, take that point in the second derivative. If it's negative, that's a maximum. If it's positive, that's a minimum. Does that make sense? Because that will tell you concavity. Or you do the analysis that I showed you how to do. You make your first derivative test. You say increasing, decreasing, increasing. And that's going to give you what type of maximum you have. Or you check the endpoints on these intervals. So that's like 3 different ways you can check. We know that all of our possible maxes and mins have to occur here, here, or there. That's it. So if we plug in those 3 values, one of them will give us a minimum. So I'm going to go back over here. We're going to check these points. By the way, when we're checking points like this, are we using the first derivative? Are we using the original function where I'm checking absolute max and min? What am I checking? The original one, yeah, because that's telling us actually the cost, the actual cost there. So I'm looking here, right there. I'll be plugging in 0. Or I'll be plugging in 8, or one of them. Can you help me out with that? 0 is 9. So this was x.
8 is 9.4.
And this is our cost, right? So 0 would give us a cost of $9. $9. Now, if this is a billion, actually a billion instead of like 1, that's $9 billion. I don't know how much it is. How about 8? And what'd you say, 8?
9.43.
Okay. How about 5 root 3 over 3?
Close enough.
I don't know. I don't know what 5 root 3 over 3 is. I'll have it written down. How many people got 8.33? 1, 2, 3, 4. Yes, yes, yes. And you all sure you're right? I love it. 8.33. Did we find the minimum? What is the minimum? Good. Okay, the minimum isn't 5 root 3 over 3. That's not what the minimum is. The minimum cost is actually $8.33. The maximum cost would have been $9.43. Right? This 9, it's intermediate, but it's definitely not the minimum or the maximum. So our minimum actually occurs when x equals 5 root 3 over 3. How much is 5 root 3 over 3 about? 866?
Yeah.
So about 2.9 kilometers. So here's what this says. If you're the one building this pipeline and your boss says, look, I gotta have you minimize the cost, which you could do, right? That's actually kind of a realistic example. If you had to actually do this, you could do it with this, right? You could easily do it. All you need is the cost. Now that's not gonna be a dollar, but even if it was like $1.38 million per kilometer at sea, you could do it. Cost there, you could do it. You'd say, okay, boss, whoever you are, we're going to go from point A, which is directly perpendicular to from the land to our oil. You're going to go 2.9 kilometers, and that's where you're going to draw the line. And you can say you're going to make your oil line from there to there, exactly from there to there. Make your land line from here to here. Have 2 people start working, meet at the middle, and that way you save the most money. Does that make sense? We definitely don't just want to guess. This right here, if x is 0, you got $9. Doesn't seem like a whole lot, but you're like, oh, that's only, what, 67
It's in
cents.
billions. That's
But if this is in
millions
billions,
of dollars you're losing.
that's $670 million, if I did my math right. It's a lot of money, okay? You definitely don't want to have 8. Oh my gosh, you did 8. That's the worst. The worst you could do is go directly from there to there. That's the worst, unless you couldn't buy all this land, and then maybe you'd have to, but that would be a different constraint. How many people understand our example here today? Good. We're going to do one more. We're going to talk about minimizing material. So this is more of a geometric approach. This had a little bit of geometry in it. This is only Pythagorean theorem. This is actually kind of a economist or maybe a business approach. This one's definitely going to be like, I don't want to say engineering because we're not doing any engineering, but dealing with more of a geometric figure, okay? So let's suppose that you're in the business of bottling Coca-Cola or some sort of cola, and you want to come up with a can that holds the most amount of soda for the least amount of material, right? So when you see a can, typically we design cans that fit in your hand, being they're easy to drink, right? But it's probably not the most, honestly, economical way that you could package something. It's actually a little bit too long. We'd have to have something more squat to save ourselves some material. Do you follow? Would you want to make a can that's like this round and this big? Drink my soda. No, probably not. Or unless you go to the Yard House, you're probably not going to make a can that's this tall and that skinny, right? Have you ever been to the Yard House?
Yeah.
Do you know what I'm talking about? They have beer that's this big. It's a yard. Right? It's this big. It's like this big. That'd be like 2 yards. But here you go like that. Okay, you're not going to do that if you want to save. If you want to look cool, then yeah, of course. But if you want to save money, like with bottling, you're not going to do that. It'd be stupid. So let's talk about. We want to bottle 1,000 cubic centimeters. Not bottle, I guess can. We want to can 1,000 cubic centimeters. How much is 1,000 cubic centimeters? Someone who's in science, you sciencey people, is that a liter? Is that close to?
Yeah.
That is a liter, right? Cubic centimeter is a milliliter, is that true? Oh, yeah, right. Yeah, we're doing right. So we want to basically can a liter of cola. Or beer, if you like beer, a beer can, I don't care. Make it exciting to you. We want to minimize the material needed to make that happen. Well, you know what? We better start with the picture, just like always with these problems. So let's start with a cold can. Cold. Hey, what are the dimensions of a can that you need to know? What shape is a can? So it's cylindrical. What dimensions do you need?
Need the radius, you need the height.
Yeah, it is circular in nature if you're looking down the top of it. So yeah, definitely have to have something to do with the radius. Also have to do with the height. For sure. So let's go ahead and do this. R is the radius. H is the height. And let's do this. Let's call S the surface area. You follow? Because the surface area is the amount of aluminum, or whatever you're going to make your can out of, hopefully probably aluminum, that you're going to need. Do you follow me on that? So surface area would be the faces, the top, the bottom, and the side of our cylinder. There's also one more thing we have. We have the V, the volume. Now, before we begin, let me ask you something. What are we trying to minimize here? Are we trying to minimize the volume? Are we trying to minimize the radius, the height, or the surface area? That's what the question is asking you. It says, minimize the material. The material is the surface area, not the volume. The volume is actually constant. Do you see that? That's the 1,000. That's not going to change. We have to have it hold a liter full of soda. Because if it doesn't, you're going to have it in your mills, or your, so is it a mill, a soda mill? We're going to soda plant, I don't know what they call it. But they're going to fill full of soda with a liter to go either overfull or it's going to be way too small in there. So we want it to hold exactly a liter. Let's talk about our formulas. And we'll talk about any constraints we have. Let's do the formula first. The formula, if we're trying to figure out the surface area for this thing, note that what we really have you ever thought about what a cylinder is? Have you ever cut a Pepsi can apart? I am, because maybe you guys are interested to see what it actually looks like. It really is just a rectangle with 2 circles on the top and bottom, right? So if you did this, you took your rectangular piece of paper and you just fold it around, and you got this, can't hold it around very well. You got the cylinder and you just close it in with 2 circles, you basically have a can. Follow? So what this really looks like, if I were to disassemble this and make the individual figures, I've got the body of my cylinder, I've got a circle, and I've got a circle. I haven't put the lids on, that's your can. So let's think about the surface area of this thing. What's the distance from here to here? Is it the same R as this?
Yeah.
Of course. Is this the same R as that?
Yeah.
It's a cylinder. How far is it from here to here? From here to here. Height. Okay. Now here's an interesting one. This is the weird one. Because we need to know that too, right? What's that? Yeah, that's the circumference of the circle. It has to wrap around the circle, right? So whatever the circle is, that's got to wrap all the way around it. That's 2 pi r. You okay with this so far?
Go back to geometry.
Geometry, yeah. Actually, some calculus is calculus and analytical geometry, which this would probably take part of that. But anyway, do you see the figures that we have? We get 2 of these circle guys that are exactly the same. We've got
Yeah, I see what you
a
mean.
rectangle that's 2 pi r long. That's a weird way to think of a rectangle, isn't it? The rectangle is 2 pi r long, and it's h high. So let's think of the formula for a surface area. It's got to include 2 tops plus 1, let's call it the body. Do you follow that? 2 tops. 2 times, now the top. We're talking about area, right? The area of these figures, because surface area is what we need here. So what's the area of one of the tops?
Pi r squared.
That's a circle, yeah, pi r squared. So would you agree that the 2 tops together are 2 times the pi r squared? Pi r squared gives you an area of a circle. We have 2 of those circles, therefore we have 2 times the pi r squared. Yes? Add to it the... the area of the body. Remember, this is surface area here. What's the area of our rectangle? How do you find the area of a rectangle?
Length and height.
Okay, so 2 pi r times the h is exactly right.
So the exact same. That's literally just the surface area formula. Interesting way of looking at it. Yes.
Feel okay with this so far? You sure? How many people do feel just fine with that? It takes some work to really think about that, doesn't it? And of course, I can't give you an example for every one that you're going to have, but the idea of going through is the same. Draw a picture, come with a formula, come with some constraints. Now, we're done with the formula. That looks great to me. Almost great. We have too many variables. We can only have one variable for this. But we're going to have to use a constraint to make that work. So the constraint. What is the constraint?
1,000 cubic centimeters.
Sure, something has to do with 1,000 cubic centimeters. What has to do with 1,000 cubic centimeters? Not the surface area. The surface area is the material that we need.
Yeah,
We
volume
know
has to
nothing
be-
about the surface area. Okay, notice that you can make the surface area an infinite number of possibilities and still come up with a liter of cola. Like I said, you could have, see if I can do this as your can, which holds a liter. Right? That would be stupid, but you could do it. You could have this as your can, which holds a liter. But we want something that's going to minimize the surface area but still hold a liter. The constraint is holds a liter, holds 1,000 cubic centimeters. You follow me? So we need to come up with a volume. We also need that volume to equal 1,000 cubic centimeters. Does anyone know off the top of their head the volume of a cylinder? It's not hard to figure out if you think about it.
Pi r squared h.
Pi r squared times the height. Circles stacked up on top of each other. Yeah, very good. And we said the volume had to be what now?
1,000.
So if our volume is pi r squared h, which is the volume of a cylinder, then we have 1,000 pi r squared h. Do you feel okay with the surface area? Do you feel okay with the volume? Which one are we trying to minimize again, the volume or the surface area?
Surface area.
So this is not what we're going to take a derivative of. We're going to use this as our tool. We're going to use this to solve for a variable, plug it into here, and take the derivative of this one, because this right here is the thing that's going to give us our max or our min. You right? What variable do you want to solve for? You want to solve for r, or you want to solve for h? Most definitely h. That's much easier to solve for. If you solve for r, you're taking square roots, plugging those things in over there. That'd be kind of nasty, right? So probably solve for the h. How do you solve this for h?
1,000 over pi r squared.
So if we do that, we get the surface area that we're trying to minimize. 2 pi r squared, we like that. 2 pi r times h. But h is now 1,000 over pi r squared. Feel all right with this so far? Do you see why we need that substitution? Otherwise, we're not going to be able to take a derivative, at least not without using implicit, and that would be very difficult because we don't have a rate of change. And implicit is not, it's not with respect to time at all, right? So we can't use that stuff. You're thinking, why don't we do that? It's not with respect to time. This is not changing. Okay, this is, we want to figure out the minimum surface area here. It's not a related rates problem at all. So here, well, we had to change it to one variable. We only know how to take derivatives with one variable. So we have the s equals 2 pi r squared plus, what's this going to give you?
2,000.
Great, 2,000, I see that. Pi's gone over r. Still all right? Probably do one more thing. What are we going to have to do next? What's the next idea?
Derivative?
It's a derivative. Now, our constraint didn't come up with any endpoints. You see that? We didn't have any. We can make the dimensions any way we want. So we're really going to have to take a derivative to find out the maximum in here, if we have one. So we're going to go ahead and take a derivative, but before we take a derivative, you might want to move what? Part of the r. Yeah, shoot, let's take our derivative. What that's going to do is give us our slope. We know that absolute maximum and minimum, if they're going to occur here, they're going to occur at a critical number, where we're changing from increasing to decreasing, or decreasing to increasing. What'd you get? Minus 2,000 what? R to the negative 2. Okay, good. I like what Michael said. He said, put it over r squared. Maybe a little bit easier to think about, right? What are you going to do with that now? That's your first derivative. What do you do? Let's do that. What now?
Solve for r.
You gotta solve for r somehow. Probably a good way to go about it, multiply both sides by r squared.
You need your minus sign.
Oh, no, I'm sorry. You know what, I left out a step.
What?
I added that. I did it all in my head, I'm
Oh.
sorry. It made sense to me. Okay, so set it equal to 0, add that over, that way you have different sides and nothing you really do at this point. Maybe now multiply both sides by r squared, that way you're going to have r cubed, and maybe divide both sides by 4 pi. Do you see what I'm talking about?
Yeah.
So that ultimately you're going to get this. Multiply both sides by r squared, you get the r cubed, divide by 4 pi. And you get 2,000 over 4 pi. Simplify a little bit. What's 2,000 divided by 4? So then r cubed, 500 over pi. I'm not really interested in r cubed. How do you get rid of the cube? Yeah, just take a cube root of both sides. That's great. Great idea. If you're looking for an exact answer, it's the cube root of 500 over pi. Now, if you work at Pepsi Cola and they say, what radius do we need? And you go, cube root of 500 over pi. And you go, seriously? Can you please tell me what radius I need here? And you're going to go, say what now? 2 point? Really? Maybe. Can you try that one more time? That's what I got.
Yeah.
What would this be in? Centimeters cubed?
542. 500 divided by pi, take a cube root of that, you're going to get the 5.4. 5.42 what? What is it? Not cubic. That would be a volume. This is a distance. Notice what you did. You took a cube root, right? You took a cube root that has cubic centimeters. That would be centimeters,
No, just centimeters.
not inches. Oh goodness. We made that inch. That's a huge can of cola. Woo.
That's like imposters.
That's bigger than that. 5.42 centimeters. Divide that by 2.54 and you get the inches, right? So you can figure that out if you really wanted to. But that would be 5.42 centimeters roughly. Can you tell me how you would find your height out?
Well, but that's the information we need to solve.
I plug it in. or
It's
something.
already solved for h. You plug it in. Believe you're going to get 10.8. You try that. Oh no, there's no way. I just remember.
He's taught this lesson before.
Yeah, 10.8.
10.8 what?
10.8.
No, 10 point, isn't it like 10.84?
2.8.
Oh.
Yeah. It's twice the radius. No, it's exactly twice the radius. Which is interesting. Think about it. This is weird, but what maximizes volume of a cube of a rectangular prism? If it's a cube, right? That's the least amount of surface area, the maximum amount of volume. A cylinder, if you had it the height as twice the radius, think about what that says. The radius is this distance. That means it would be the height times the height. That would basically be kind of a cylindrical version of a cube. Do you see that? That's interesting. Kind of weird. Now you could prove that it is twice the height is twice the radius. You do that. What I want to do is more calculus. We have no way of verifying that this is actually a minimum or maximum right now, right? You're just guessing. What if you accidentally minimize that you didn't? What if you maximize the surface area? This is minimized. But how you do it, just go ahead and take another derivative here. That's going to be 4 pi
Plus
6,000 over r cubed. Did you follow me?
No.
Yes, no? Are you with me that that's the second derivative? What does the second derivative give you?
Huh? Is it that? How's that not 4,000?
Okay, so plug in the R that you have. Now remember, we're not worried about the actual number, we're worried about whether this is positive or negative. So think about this. If I plug in 5.42, it will give me a concavity. True? It will either tell me concave up or concave down. It won't be, most likely it won't be an inflection point. So if this is 5.42, 5.42Q is, I don't care, but it's positive. 6,000 over a positive is a positive. Add things together, this doesn't change, right? 4 pi is positive. Positive plus a positive is a, would you agree that at R equals 5.42, this is concave, what is it? Up. Because this is greater than 0. So if we're concave up, and this is the point where we change increasing, decreasing, or decreasing, increasing, which we actually didn't check, that would have to be this point. Right? That have to be that point. So is that an absolute minimum for us for this range? Yes.
Mm-hmm.
Yeah, that's the minimum. We just minimize the surface area and you prove it. The other way you prove this is you put this on your first derivative and you check 2 points, one to the left and one to the right. You check like
Is that really
something
6,000?
like 5 and 6, and you say, oh, it's decreasing, that's increasing, that's got to
Yeah,
be a
okay.
minimum. That's the other way you can check it. How many people feel okay with our, well, let's, good.
Yeah, it should be
Okay, yeah, my
4,000.
bad. This actually should be a 4,000, not a 6,000, as previously on the video. I accidentally multiplied by a 3 instead of a 2, so the negative 2 times the negative 2,000, that's what's giving you the 4,000. All right. We start chapter 4. Chapter 4 is, like I said, a switch from chapters 3 and everything before, where we used derivatives before. We're going to be using something different, chapters 4 and 5, which is going to end our course. In chapter 4, we discussed the second of the 2 main problems in calculus. The first main problem in calculus, where we spent the majority of our class, I mean more than half of it, was can you find the slope of a curve at a point? What was that? Derivative. The second question in calculus wasn't about the slope of the curve at a point. It was, can you find the area under a curve? Do you remember that question? I introduced it, I think, like the first day of real calculus. I said, can we do this?
Real calculus.
Given some sort of continuous function from A to B, can you find out what the area is between that curve and the x-axis, or basically the area under the curve, from here to here? And the answer is yeah. Yeah, and we actually have 2 ways to do it. I'm going to introduce to you what's called the rectangular method today. We'll deal much more with it in section 4.4, 4.3, and 4.4. They're kind of tied together on how to actually do this with the rectangular method, but I'm going to introduce it to you today. And then we'll talk about what's called the antiderivative method, which is a more concise way to do it. Are you ready for it? So this, I'm going to kind of go in a weird loop. I'm going to introduce this with the rectangular method. We'll talk about antiderivatives, then I'll use rectangular method to kind of prove what we just learned about antiderivatives. You follow me? So we have to wait till 4.3 to prove some of the stuff I'm talking about here today. I'm going to give you kind of an intuitive approach on it, though. Hopefully it makes sense for you. So first method, let's talk about the rectangular method and at least the idea behind it. So rectangle method. Rectangle method says, well, why don't you divide your interval into n, some number, n, equal subsections, equal as far as their width goes.
They're what?
And equal subsections, equal as far as their width goes.
Okay.
Subsections, subintervals, whatever you want to call it. and create a rectangle. Rectangle in each subinterval, in each subsection.
A rectangle?
Hence where we get the term rectangle method, or rectangular method. So here's basically the idea. Let me redraw the picture for you. Let's say that I make this a little bit bigger too. Here's my graph. Here's my interval. The idea behind the rectangle method is, can you find the area under this curve the way it is?
No.
No, not really.
You can't have
Because we
super
don't have a
small
formula for this, and even
rectangles.
if we did, it doesn't have straight sides. And literally, we know how to take an area up till right now in geometry is if a figure has straight sides, right? Whether we can break it up into rectangles or triangles, because we know how to take the areas of those figures, or perfect circles. You know how to take the areas of those figures. This is not a regular shape that we know of. It's just some random function. In fact, I haven't even been specific. It could be any function. But the idea is, let's go ahead, let's break this up. We'll say, okay, we're going to split this up into however many parts we choose. Let's just assume those are equal widths.
How many did you put? 5?
That's about right. And says if we have some sections here, what we're going to do in each section, since they have equal widths, so I'll tell you why we need equal widths later on in section 4.3, 4.4. But right now, let's just assume we have some equal widths. That's so our bases are all the same. Our rectangles, equal bases means they're easy to add together. That's basically it. So for each interval, subinterval, let's make a rectangle. Now there are several ways to do this. I'll show you one way. The problem is now, you got to determine how you're going to have the height of our rectangle. So one way to do this is to use what's called left endpoints, another way is to use right endpoints, and the third way is to use midpoints. And here's what that means. You go to the right endpoint of your interval. Here's my interval. I go to the right endpoint. I'd say I'm going to go up to where that touches my figure. Does that make sense to you? A left endpoint would say I'm going to go up to where my left point
So this
touches
could be
my
like a
rectangle.
plus-
A midpoint would say
or no,
go to the
y.
middle, see where that touches
A plus
the
2y.
figure, and then make your rectangle. That would determine your height. So we have left endpoints
So you gotta decide how.
where that touches. Right
What your width
endpoints
is.
where that touches, or midpoints. Let me show you the midpoints, and here's how you do it. You go, okay, from my midpoint, I'd go up here where it touches that f of x, wherever my function is. That's where I cut it off, and that makes my rectangle. Does that make sense to you? Why do that? Well, it's actually not going to matter when we finish 4.4. We'll talk about what's called the definite integral. It doesn't matter whether you use left, right, or center. But for us, if we are always using one endpoint, sometimes we can systematically underestimate the area, and that would be a problem for us. Then this one would go, okay, let's go up. Where that touches, I'll draw the top of my rectangle, finish it off. And you would do this for every interval that you have. How many people feel okay about the idea here? The idea of drawing rectangles there. Do you see where the midpoints come into play here? The midpoint gives us the height of our rectangle. That's going to be useful when we get down to 4.3 and 4.4. Very useful. Now, how would I find the area of this figure? The approximation of this area? What would I do with this? If we know the area of a rectangle, which we do, right? A rectangle is just a geometrical figure. If I can find this area, and this area, and this area, and this, if I can find all the areas of all my rectangles, all I have to do is add them together, and I'm going to get at least an approximation of the area of my figure. You follow me? Now, is it going to be exact? Well, you can tell it's not. I mean, sometimes I've overestimated, sometimes I've left out some area. Sometimes it's about right, but sometimes, and I don't know whether I'm perfect or not. So I'm not going to be exactly right. It'd be a miracle if it was exactly right. It's not going to be a miracle. This isn't Harry Potter mathematics, so magic doesn't happen in math sometimes. But anyway, that's another topic, I suppose. It's not going to be exact. It's going to be an approximation. Now the question is, how can I make this better?
Smaller rectangles?
So would you agree that the more rectangles I have, the better approximation this will be? So, I mean, here I had 1, 2, 3, 4, 5, I had 6 rectangles. If I had 100 rectangles for the same width, 100 rectangles mashed up in there, I'm going to underestimate by a lesser of a margin, right? So the more rectangles I have, the better approximation becomes. So as the number of rectangles n goes to infinity, or as the space between the rectangles goes to 0, right? Does that make sense? If there's a space, as this goes really, really close to 0, that's the idea of a limit. As that goes to 0, then I have a very, very good approximation. In fact, it's so good that it's exact. So the idea here is cut your region into rectangles. Every rectangle, you're going to take the area of that. Add all the rectangles together, and you're going to get a good approximation of your figure. How do I make it better? You let the number of rectangles go to infinity. The way you do that is let the space between them go to 0. For a better approximation, make the space between each interval Notice that in this context, the space between each interval, that's the width of a rectangle. Approach 0. And again, the idea is, well, think about it. If you have a finite distance, A to B, and you let the distance of each subinterval go to 0, how many rectangles are you going to have?
Infinite.
If you have a finite space and you let the distance between here and here go to 0, you can pack in an infinite number of rectangles, right? If you pack in an infinite number of rectangles, you will have no
that's an
over
interval.
underestimate. It'll
Awesome.
basically be like finding the area under a distinct point, which is impossible. You can't do that. But if you say it's really, really, really small, and you can put paper between it, then it'll be exact. And that's the idea. That's the limiting factor. Same, it's kind of basic concept of a derivative, right? Where we take the distance and made it 0, and we're taking the distance and making it 0. Very similar idea. Only now we're talking about an area instead of a slope. How many people understood the idea of this? Good, good, that's fantastic. More on this in section 4.3 and 4.4. This is all you get for right now, just a little taste. This is appetizer. Are you satisfied? No, of course you're not. That's why you need more of a meal. This is the meal, okay? Different method. Antiderivative method.
Practice that line really good.
No, I just made it off the top of my head. Pretty good, huh?
Nice. Improv.
I suppose if that's the appetizer, this is like the salad and the main course, and we tie it all together with the dessert. And then the chapter 5 is icing on the cake, baby. Just how to use it. If you like cake.
Insert your favorite dessert here.
You don't put icing on creme brulee. Burn it. You do, burn it. Anyway, antiderivative method. This I'm going to go a little bit past where the book takes you. The book has you do just what antiderivatives, how to do antiderivatives. What I'm going to do is tell you what an antiderivative stands for and then how to do them. You're going to find out now, I'm going to prove this to you after we do 4.3 and 4.4, so I'm going a little bit beyond. That if A of x, here's kind of the special deal, here's what you find out, the end game of section 4.4 is this basically. If A of x stands for the area under a curve, for some function. If A of x is the area function for some f of x, some curve like this, for f of x, on some interval, I've got to give you an interval, otherwise you can't find an area. Does that make sense? You have to have an interval.
Yep.
Areas are a definite thing. We'll talk about definite integrals later on, but areas are definite. You have to have points, not numbers. Then here's what I'm going to tell you. It's kind of a very cool thing. This is where we're going to end up. Again, I've said it 5 times now. This is where we're going to end up after section 4.3 and 4.4. You get it? We're going to end up with this statement. Which is a fantastically marvelous statement. It's magical right now because you don't know the concept behind it, but it's magical. What it says is, this thing right here is an area. This thing is an area, right? It says if you take, this is kind of crazy to think about, but if you take the derivative, that stands for derivative, right? You take the derivative of your area function, it will give you your original function. It will give you the line, the curve. So basically it says this: if your area function represents the area, take a derivative and you get the function back. Does that make sense to you?
No.
It shouldn't really, not that much.
So-
I'm going to prove this to you later. I'm not proving it yet. What you need to know right now is that if you are given an area function, take a derivative of that thing and it will give you your function back. Well, now that's cool, but we're never going to start with this. We're always going to start with our line, right? That's what we want to get to. So, well, this implies this thing. This says, if we want to find the area under a certain function, we basically need to be able to undo this. We need to undo a derivative.
derivative, that makes sense.
For some interval, let me go through this one time for you so you kind of get the interplay here. Here's what it says.
What do you,
It says the area of a curve is a of x. What I know for
Oh, I
sure
see, I
is
see, I
if
see.
I take the first derivative of the area, that's equivalent to my curve itself. So if I want to find
So-
the area under my curve, this statement's true, right? The first derivative of the area
basically
is the function.
undoing the function.
So if I want to find the area of the curve, under the curve, what I'm going to do is undo the derivative. That gives me the area. So basically, here's the idea. You pretend that your function is a derivative. If you undo that thing and treat it like a derivative, you're going
That
to
gives you
find
the
what's
area.
called the antiderivative. That is the area under the curve. That's the idea of the antiderivative method.
And that doesn't make
We'll
sense.
get more into it in a second. I'll prove it to you. I'll prove it with an example. I have to prove it to you with 4.3 and 4.4 later on. I'll prove it with a couple examples. So, if we're going to find the area under the curve,
So the
under f of x,
antiderivative
we
is
must
the
undo
integral.
a prime of x to find a of x, the area. Would you like an example that you can actually kind of see? I was hoping you'd say that. Have I lost you yet?
Almost.
You get this, right?
Yes.
Oh, good, good. Now, this is not what we're talking about today, so it's good for 4.3. Did you get this? No, you don't yet. Trust me, you don't. You won't get it fully until 4.3 or 4.4. The idea is, can you find an antiderivative? I'm going to teach you that in a second, but I want you to understand the concept behind it as well. The concept is we're trying to find the area under a curve. That's why I gave you this introduction. That's the idea, so I'm trying to get that in your head. Remember how I always kept saying, what's a derivative? What's a derivative? You're like, oh my gosh, slope of period point. You know that, right? Good, because I pounded it in your head, and that's when we do the same thing here. What we're doing is we're finding the area under a curve. That's what an antiderivative is. What I've told you, and I've done it without proof, I'm not going to prove it till later, I've told you this. I said, the first derivative of your area is your function. So if I can undo my function by treating it as a derivative, I will find
the
the
area
area
function.
function. So basically, we
Awesome.
need to go backwards from a derivative. Did you get that? If the function is the first derivative of the area, that's what that says. The function is the first derivative of the area. If I can undo the derivative, I get my area. That's the idea.
Yeah, that doesn't make sense why the
That's the antiderivative method in a
derivative
nutshell. Very quick
area function
statement.
equals
Now,
0.
let me do some of
Original
this with
function.
geometry
It's real.
to show you that it does in fact work. Then we'll get on into some antiderivatives and how to do those things. So, example. If we have a function f of x equals x plus 1, I'll give you something easy to graph because I'm going to show you the graph in a second. I want us to find the formula for the area on 1 to x. Now, this would kind of be stupid if I give you just 1 to 3 because we could just use the triangle and find the area. But what I want to find is 1 to x, and I'll show you why this works according to that. First off, can you Can you graph this? First off, can you graph this? Geez, I hope so. What's your y-intercept? What's your slope? Would you agree that that is your function? We're trying to find the area between, what did I say, -1? Oh, you know what? I want -1. Let's make that negative much more interesting. -1 to x. Now, I don't know where x is. I made it positive, but it doesn't have to be positive. What we're talking about, wherever this x is the area of that shaded region. Now, keep in mind that this function is x plus 1. What shape is that? Can you find the area of a triangle? Of course you can, yes. Let's find the area of a triangle. The area, in terms of x, notice I'm using the same terminology I used over here, right? That's an area function. The area in terms of x, wherever x happens to be.
Alright, I'm gonna stop here.
Is, how do you find the area